Hello, and welcome to the Building Interactive Data Visualizations with D3.js video course by Pact Publishing. I'm Michael Westbay, your host and guide for this video course. This video course was put together by Alexander Simos and I. Alexander is a programmer working directly at the intersecting fields of data science and data visualization. He has used D3 for many projects of his own, as well as for the creation of an open-source charting library called D3+. My background is in computer science, with an emphasis on databases, spending most of the past 20 years connecting databases to web technologies. We'll start off in Section 1 by setting up a development environment in which we can run D3, including the obligatory Hello World script. After working in the browser's interactive console to get a feel of the difference between elements and nodes, we'll conclude the first section by demonstrating the difference between driving a document in raw JavaScript compared with D3. With manipulating the DOM, Document Object Model, out of the way, Section 2 takes us through the steps of planning a page, creating a data structure, and having D3 drive the creation of the page from its data. It's all about data-driven documents. In Section 3, we learn about SVG, scalar vector graphics, and how to draw on the canvas using both raw JavaScript and D3. Once we have drawing on the SVG canvas down, Section 4 introduces us to drawing a simple bar chart with SVG rectangles and random data. Section 5 features a scatterplot graph, complete with axes and labels alongside the data points, where the data is fetched from an external server's dynamic API. Now we're cooking with fire. We then take our scatterplot from Section 5 and add interactivity in Section 6. We learn how to handle user events, update our data with a new query, and, in Section 7, animate the changes in our graph, including literally dropping data points that no longer exist. In Section 8, we build a choropleth, that is, a world map using shading to indicate the quantity of exports for a given country. To accomplish this, we go from fetching and preparing the map data set through to zooming, tooltips, and building a legend. Finally, Section 9 puts everything together that we've learned by creating a geoscatterplot, that is, a scatterplot graph where the points are made up of country shapes of similar size. The graph is fully interactive, allowing the user to specify the year and export product for each axis, as well as get details from a tooltip by hovering over a given country. That's a great deal to cover, so let's get started. Hi, my name is Michael Westbay, and I'll be your host and guide throughout this Building Interactive Data Visualizations with D3.js course. D3 is a sophisticated tool for building data visualizations in the browser. So let's have a look at today's game plan. In this video, we'll help you understand what D3 is as we cover a bit of its history and discuss some of its defining characteristics. We'll wrap things up by installing the library on our local computers and write our obligatory Hello World program using D3. D3 is a library written primarily by Mike Bostock, and follows largely in the footsteps of other front-end visualization toolkits dating back to Prefuse, which required a Java plugin in the browser. That was followed by Flare, which required Flash, and then Protovis, written solely in JavaScript, up to where we are today with D3.js, which has become the de facto standard on the web for building interactive data visualizations. There are a lot of visualization libraries out there: Raphael, Paper.js, Processing.js, and JavaScript InfoVis Toolkit, to name a few. So why use D3? To start with, it works with web standards and existing web technologies to allow users to manipulate any part of the DOM. Thus, it is as flexible as the client-side web technology stack, HTML, CSS, and SVG, making it more of a toolkit than a purely graphics library. The name D3 stands for Data-Driven Documents, hinting at the library's usefulness beyond graphics and any web-related content paired with data. Relating to this previous point, since it works well with web standards, it can also work in tandem with other JavaScript libraries that you may already be comfortable with, such as jQuery or Backbone. The most important part, and why it is such a powerful tool, is that it takes a low-level approach to data visualization, giving users access to the raw primitives of building charts such as bars and lines, as well as higher-level concepts such as axes and zooming behavior. D3 does not limit a developer's creativity by using pre-built charts. It gives developers control over the smallest elements of the chart while allowing seamless binding of data to DOM elements. Thus, D3 acts as a perfect agent between data and DOM elements. The last 2 points are also important for anyone thinking of the future. Since D3 is being very actively maintained and has such a large community, it makes it a good candidate for a technology to invest in. Here we are at the D3.js.org homepage, a great resource for documentation and examples. We're going to download the library via this link, d3.zip. Now we'll create a folder for our first D3 example to live in. From the terminal, we'll run a simple HTTP server via Python with the command shown here. Here we'll create the world's simplest HTML page, just something to show us everything is working. So we have our basic HTML template with our link to the D3.js library. And to prove that it's working, we'll write a simple example, selecting the HTML body, appending an h1 tag, and setting its text to Hello World. By navigating to localhost at port 8000, we will be able to see the root of our directory where our server is running. And if we click on the helloworld.html page we just wrote, we'll see the results. Great! It's working! As we can now see, we have a local server running, serving us HTML and JavaScript files from a basic template. We've accomplished our mission of writing and running a program in D3 and are ready to move on. We have now learned a bit of the history and background to the D3 library, downloaded it, and served up an HTML file locally using the Python simple HTTP server. In the next video, we'll show how using the browser's built-in console can help us develop and debug our JavaScript code. Following that, we'll take a look at a side-by-side comparison of raw JavaScript and D3 to see how it makes common tasks much easier. In this video, we'll learn how to activate our browser's console to learn a bit more about what's going on when our JavaScript is run on the client. Programming for the web with JavaScript is a bit different from programming in more traditional languages due to the fact that we must use another application to see the output of our script. This is where the console comes in. Using the console, we are able to not only use it as an interpreter to execute live code, but also use it to print statements to see a snapshot of our data as the program is running. By the end of this video, we'll be comfortable debugging our programs within the browser. We'll start by learning how to activate the console. Then we'll look at how to execute code right there, live in the browser. While we're doing this, we also learn the difference between HTML elements and their representation as nodes in the DOM, that is, Document Object Model, which is how JavaScript sees the elements. Finally, we'll return to our Hello World example from the first video and modify this to print debugging statements to the console. Let's jump in! To open the console tab, we can do one of the following. Using the keyboard, we can just press Command-Option-J on a Mac or Control-Shift-J on Windows or Linux. With our mouse, we could select View, Developer Tools, JavaScript Console from the top menu in Chrome. While keyboard shortcuts are the same for all open source-based browsers, that is, Chrome, Firefox, Safari, and the numerous WebKit-based browsers in Linux, menu options vary, with Safari actually requiring one to enable developer tools in its property dialogs. Whichever method you use, you should now have a new pane at the bottom of the page. Or if you've got the screen real estate, you can open it in a separate window or as a split screen on the right-hand side. Nonetheless, the console is a very powerful and comprehensive tool. Please note the many different tabs across the top. These allow web developers to see what's going on under the hood. For much of this course, we'll be focusing on the Elements and Console tabs. Becoming familiar with some of the fundamentals of the document object model will make our time with D3 much less frustrating and much more rewarding. At its core, the main objective of D3 is to allow us to manipulate the DOM dynamically with our data. But before we can go there, we should first have a grasp of what the DOM is and how to manipulate it. Don't worry too much about understanding every detail here. The point is to give an overview of what D3 does behind the scenes for us, and to become comfortable with the console. HTML and JavaScript work very closely with one another. One is the markup that tells the browser how to visually represent our data. The other provides us with logic to manipulate it. Elements are those tags that you see in an HTML document. That is, body, div, h1, etc. What is not so clear to a human looking at an HTML page, but is how JavaScript views the document, is that each element is a node, and there are further nodes that don't have a clear notation within an HTML document. The global variable document, for example, is the root node of a page. It may contain the document type, processing instructions, comments, and the root element of HTML for HTML documents. This is how the document object model, or DOM, works. Let's load our Hello World page from the previous video into our browser and pull up the console. Now type document into the console and hit enter. This returns the contents of the document node under which the HTML document's doc type and HTML element reside. We can use instance of, a handy function to tell us if our variable is a certain class. So let's enter document instance of node. True. How about document instance of element? False. Document get elements by tag name h1 returns an array of one h1 element. How do I know it's an element? Enter document get elements by tag name h1 sub 0 instance of element. It also returns true if we check its instance as a node. What about its first child? Document get elements by tag name h1 sub 0 first child. That looks like text. Is that an element? No. Is it a node? Yes. So what do we now know about the DOM? Well, it is a set of nested nodes, some of which are HTML elements. This is what we're going to manipulate with D3. I encourage you to explore further on your own. Returning to our Hello World example, we have the result of our line that outputs Hello World placed into the variable h1. Now let's output that to the console. This results in an object containing an array with our h1 element that contains a text node of Hello World that we created. We can access that same information simply by typing h1 in the console, as the variable survives the end of the script. However, that is not always the case. Using console.log within a program is a useful tool to get a snapshot of the DOM at any given time for inspection within the console. You'll find that this method of logging data and DOM nodes as they are processed is at least as efficient at tracking down bugs as pausing the processing of a script in most cases. So, what have we learned this time? We've learned a great deal about the console and how JavaScript represents our HTML page within the DOM using nodes and elements. We saw how to access the underlying nodes from our D3 selections via console log statements for debugging. These may seem like trivial tasks, but they are important building blocks for moving forward with more advanced features of D3 and JavaScript. In our next video, we'll dive in a bit deeper to look at some of the differences between D3 functions and raw JavaScript. Similar to the previous video, we'll be building up our JavaScript fundamentals. We'll do this by looking at various ways to perform common tasks in raw JavaScript and then show the D3 equivalent. We'll do this by writing code in our boilerplate HTML page and then running these examples in the browser with our console activated to see what the results of our actions are. One of the most basic tasks that is required for almost all of our scripts moving forward is learning how to create elements. We'll look at how this is typically done with JavaScript and then show the D3 way. After this, we'll look at how to select elements and work with groups of those elements. Then we'll investigate the difference between changing the attributes and the styles of an element, also an incredibly common task. Finally, we'll create a function to toggle classes to show how this can be applied to both attributes and classes. Let's start with the basics by copying our Hello World HTML file to index1.html. Within the script, let's just create an HTML element and add it to the page. We've actually done this already in the very first video, but let's take a step back and see how we can do this with raw JavaScript. HTML is just a loose flavor of XML, and since XML documents form a tree structure that starts at the root and branches to the leaves, the JavaScript API for traversing this tree-like structure relies heavily on methods like firstChild, lastChild, and appendChild. So we'll start by getting and storing our body element as a variable. We then use the createElement function on the document and supply the tag name that we want to create as the argument. We could have used any HTML tag here, such as span, div, h1, etc. But let's make it a paragraph, or p tag. Next, we create the text node that contains the text we would like to display. Remembering the difference between nodes and elements from the last video, nodes are the generic class from which elements extend. Thus, creating HTML tags and text nodes use different functions. We can then append this text node to the p element, and then append the p element to the body to output it to the browser page. To test this in the browser, enter localhost:8000/index1.html into the URL bar. Hit enter, and we now see the paragraph element just as we had created it. Now we'll perform this same exact task using D3. We can complete this whole task in one line. We'll break it up for legibility. But what took us about 5 lines of raw JavaScript is reduced to a single executable compound statement. We select our body, append our p tag, and set its text. Let's refresh our browser, and great! 2 paragraphs! Now that we have our new elements on the page, we may want to modify them in some way, either by editing their attributes or by changing their styles, that is, CSS rules. We will start in raw JavaScript by setting the class and style attributes on our first paragraph. As you'll notice, the syntax for setting these two attributes are quite different. One involves passing arguments to a function, while the other consists of setting a variable. Next, we'll perform these exact same actions using D3. D3 uses a much more consistent syntax in which attribute and style are both functions that take the name of the attribute or style you are looking to set as argument 1 and the value you wish to set them to as argument 2. Great! Now let's run these most recent changes in the browser and make sure they work. Clicking on the magnifying glass in the top of our console, then our first paragraph to view it in the source shows that it does indeed have the classes we set it to. A somewhat tedious task that is all too commonplace when dealing with the DOM is performing a certain action on a group of elements known as a node list. Say, for example, we want to set the font size on both of our paragraphs to be 20 pixels. We'll need to first select our node list, then loop through the set to set the font size for each one. If we were to set the font family for all of the paragraph styles to sans serif using D3, we could simply use the select all function to grab the D3 selection of all elements that match our criteria and set all of the styles using the same syntax that we would if we were only setting one. Now, if we run these in the browser, we'll see they both work. Our text is larger and our font is now sans serif for both. Another common task that is a bit cumbersome to perform in raw JavaScript is toggling classes. To do this, we will first get the classes of our original paragraph element and put them into an array using the split function, supplying a space as delimiter. We will then use the filter function on this array and only return classes that do not match favColor, the class we are looking to remove. We can then reset the paragraph's class name to this new concatenated string of classes. With D3, we'll perform the opposite action, adding the favColor class to our second paragraph's element. This is a much easier task using D3's classed function, which takes the name of the class as the first argument and true or false, depending on whether we want to add or remove this class, in the second argument. After reloading the page, if we inspect these elements in the console, we'll see that the second paragraph now has the favColor class and the first paragraph does not. And that concludes our Getting Started section, where we set up our environment, interacted with the browser's console, and explored working with the DOM. Next, we will move on to using these core concepts to begin drawing shapes on the page, eventually adding data to the mix to create a dynamic data visualization. But remember, having a core concept of how the basics work will benefit you immensely down the road. Building off the fundamentals from the previous section, we'll now put them to use in creating a dynamic page built entirely using D3. The data we will use to drive the page will be in the form of a JSON array. This will get us ready for using D3's AJAX methods to query the server for data. Here's what the page will look like once we're done with this section. It is a single-page site with a list of our favorite flowers, color-coded by their ease of growing. This may look like a simple HTML page, but we will step through the stages to get here, starting with constructing our data and page, then concluding the task by adding the legend shown at the bottom of this page. It's an incredibly underrated but useful task to spend time planning any project before diving in. For that reason, today we're going to talk about how we're planning to build the previously mentioned page. After that, we'll talk about the structure of the data we will have to drive the creation of the document. We can then start working on the baseline code for our page, appending new elements dynamically based on our data structure. We'll wrap up by inspecting these elements in the browser and show that the code we just wrote is working, though we won't yet see any output on the page itself. Let's start planning the page by writing down the things we would like the page to have. This will help inform our data structure. First, we'll need some sort of list for each of the flowers. Next, it would be nice to have images to go along with the flowers' names. At a glance, we would like to know which are the easiest flowers to grow. Finally, and most importantly, we'd like our page to be dynamic enough to accommodate any number of data items so we can add or subtract items without needing to reconstruct the page. Great! Now we've created our plan of attack. The next problem to tackle is to determine what our data structure will be. We already said that the list will be an unknown length, so we'll use an array to hold each item. But what will the fields be? For the sake of simplicity, let's say we'd like to have the following fields of data for each data point: its name, Latin name, light source required, and ease of care on a scale from -5 to 5. This is what our hydrangea will look like. To start working with such data, let's copy our template.html to index2.html and enter our title as My Favorite Flowers in both the header and body. We can then copy and paste the flower data from our flowers.js file into our new index2.html files script section. We'll then assign our array of data to the div elements we are planning to create. Although the amount of code we will need to write is not substantial, the order of our commands is extremely important, so we'll break this task down into 3 steps. 1. Select our container element. 2. Assign our data. 3. Enter in our new elements. Let's break this down a bit. We will be using the D3select and D3selectAll methods a lot, as these are an integral part of how D3 works. You can think of these methods as similar to the jQuery $ method or the native document.querySelector, if you are familiar with those. If not, think of them as a quick way to target any element or series of elements in a page using the same notation as CSS. That is, a .name selects classes, and a hash mark with a name selects tags by their ID. D3's select all will even select elements that don't yet exist, as you'll see shortly. The enter method is also a core paradigm of the D3 library. It executes a set of operations on the portion of specified data that is not yet bound to a selected item. Given our array of 5 flowers in our data, those 5 items get bound to the 5 divs in our select all. However, those divs don't yet exist, so the first time this is run, the functions chained to enter will get executed 5 times. Should enter be called again on the same selection with 5 data items, the chained commands will be ignored. Let's run this in our browser and take a peek into the console inspector to make sure that our new elements have been added to the page. There they are! They have been! We had 5 objects in our data array, and 5 divs have been added to the content div. Drilling down in the inspector to view the properties of one of the given divs, we find that the data property holds the data responsible for entering the div. That's how the data is bound to its element. Excellent! Wrapping up, we came up with an array of flower objects to drive the creation of our page. Using that data, we created 5 div elements on our page, each one bound to one of the 5 flower objects in our data. In the coming videos, we'll add a bit more functionality and styles to make the page display all the content from our data. In our previous video, we concluded by showing that our page was rendering our HTML div elements based on our data. In this video, we'll go a bit further and talk about how we'll add the rest of the information within our data to the page, along with a bit of CSS styling to make it look nice. Before we dive into adding the rest of our data fields to the page, let's come up with an HTML structure for what we want each data point to display. This will help us a little bit when we try to transform the static HTML into a page created dynamically using D3 JavaScript. Based on the data fields that we have, name, Latin name, type of light required, and ease of care, we model our HTML statically, as this will help us when we try to create these elements dynamically via D3. The things to notice here are that all of our data points will have their own parent div with the class flower. Inside this will be 4 nested HTML elements, the exception being our Latin name that we want to be wrapped inside of an I tag for emphasis. Once we've typed one of these into our HTML document, let's copy and paste it a few more times into the page to help us write our CSS styles and make the page look a bit more designed. Loading the page in the browser, we'll see something like this. Now it would be nice if these items appeared in a row so that our users wouldn't need to scroll and we can maximize the width of our page. Let's add the following CSS rules. Now our page looks a bit nicer to the eyes. Now that we're happy with our page layout, we'll create the aforementioned HTML via D3. But first, remove these static divs from the page. To review what we have, we start by selecting our parent element, attaching our data array, then enter the new divs, appending them to the page. The variable div now holds the array of flower divs. Inside each flower div, we want to first output the name of our flower in a level 2 header or h2 HTML element. After the div is initialized, we can simply say div append h2 to add this h2 as a nested element within our div. As for the text of the second level header, we'll want to use the text method and output the name of the flower. But how can we set the text node as a different string for each of the 5 elements in our data array? The solution is that the text method, as many other D3 functions, are overloaded, meaning that they can take various types of parameters. This is a common design pattern that we will be using constantly throughout these videos to pass an anonymous function where the first argument it receives is the data, and the second is the index of that item in the data array. To discover what we have available, we can run a simple test, outputting the data and its index to the console each time the text function runs. Reload the page in the browser. Here we see our index, starting from 0, followed by our data object exactly as it is in our array. So, in order to actually set the text in the text method's anonymous function, we will need to return the string we'd like shown. In this case, data.name will do. Refreshing the browser again, we'll see each flower name in a row. Excellent! Our next task is to create a doubly nested element I inside a paragraph element. Here I can show off another common design pattern you've no doubt already noticed, called method chaining. Since most D3 methods return a selection, we use this chaining technique, which saves time and space in our code. One important caveat is that the order or sequence of the functions matters. The next element we'd like to nest inside of our div is an image. This is accomplished in a similar fashion to setting text. We'd append an image to the div, but the dynamic content here is the source attribute of the image tag. So instead of using the text function, we'll use the attribute function, again passing an anonymous function. If we take a look inside of the image directory, we'll see that the names of the images are the same as the .name attribute in our data. Isn't that convenient? The only difference is that we've capitalized our names in our data, so we'll need to use the JavaScript's toLowercase function. As an aside, notice that we're using just D for the data parameter in our anonymous function, and dropping the index. D, representing the data, is common practice. And when the index isn't used, leaving it off saves even more space and typing. The last item, the type of light required, will be similar to the header element we created earlier. If we save our changes and refresh our page, we'll see the beautiful flowers in bloom. The only attribute from our data that we haven't addressed is the ease of care variable. We'll save that one for the next video, since we have something a bit more complicated in mind, mapping this integer to a color and setting that as the background for each flower's div. For the final video in this section, we'll finally deal with our last variable, ease of care. Using a dynamic color scale is one method to rate the ease of care for our flowers at a glance. Where we left off last time was with our page being rendered based on our data, taking an array of any length and transforming it into HTML using D3's interperidium. To continue from there, we're going to start by looking at the documentation for D3 scales to see how we can appropriately select one to use for generating a smooth gradient of colors. After we implement this, we'll test it in the browser. Finally, we'll use it to set the background color of our flower divs. Let's head over to the D3 homepage. We'll navigate to the documentation and click on API. Here, if we scroll all the way down to scales, we can click on linear, since this is the type of scale we'll be wanting to use. In particular, let's take a look at this color scale example right here. If we were to read all the documentation on the page, which I do suggest doing, we'd learn that this first line, D3 scale linear, initializes a linear scale. The domain, that is, the range of values that the scale can expect as input, is then applied to the scale via chaining. The last line sets the range of the scale, which maps to the bounds of what our expected output should be. To get a bit more familiar with how a linear scale works, let's turn to the console and play around a little. Let's load up the last version of our page in a browser and enter this into the console. Now, calling the color scale for 0.5, that is, halfway between 0 and 1, we get an output value of a color somewhere between white and green. Color of negative 0.5 is a shade between white and red. If the provided input is outside of the range, the output will fall to the lower or higher end of that range. This code snippet makes for a great starting point, but it's not exactly what we're looking for. We need to change the domain to go from -5 to 5. So let's make that change and put it into our page. Now, the same way we were passing an anonymous function to set the text nodes of elements and source attribute for our image tag, we can also do this for style. So let's pass an anonymous function to set the background color style of our div. Let's refresh our browser and see what it looks like. There we go. We get various shades of green for easier flowers, closer to 5, and reds for more difficult flowers, -5. The final component for our gorgeous page of flowers is to have some sort of key or legend to show our users what the colors mean. We'll use everything we've learned so far to do this. Let's start by creating a div with a title Ease of Care Legend. Next, like we assigned data to our divs and entered them into the page, we'll do the same here with span elements. To help us here, we'll use D3's nifty range function, which outputs an array of the integers between the first and second arguments. In this case, we want to go from -5 as our lower bound up to, but not including, 6 as the upper bound, thus producing an array of all integers from -5 to +5. Now all we have to do is set the span's background color style and throw some CSS styles to give each span some area. Then, reloading the page, we should see the span's blocks on the page. Still, wouldn't it be really cool to see the actual values of the colors represented? Easy enough. Let's use an anonymous function inside of a text function on our spans to output only the limits of our range and 0. We've learned a lot in this section. We should now feel comfortable in dynamically adding elements to the page using data and setting their text, attributes, and styles based on attributes in our data. This will all become extremely useful once we start drawing and building dynamic data-driven visualizations. But the next stop on our journey is to learn about SVG, Scalable Vector Graphics, and how they can be used on the web. We've now graduated to the third section of building interactive data visualizations with D3, getting ever closer to creating our dynamic data visualizations. In this video, we'll discuss what SVG is, how it differs from other image formats, and show how to create graphics dynamically in the browser. SVG stands for Scalable Vector Graphics. Such graphics are different from other image formats such as JPEG, GIF, or PNG. The latter formats are raster images, or bitmaps, meaning that they have a fixed resolution and cannot be scaled from their initial size without the introduction of pixelization. Vector graphics, on the other hand, are resolution independent because they are merely instructions based on mathematical formulas to be rendered by software to produce graphics. Therefore, we can zoom in on vector graphics infinitely. Scalable vector graphics are great for data visualizations for a number of reasons. First of all, as we just mentioned, they can be scaled to any size we want. So whether the user is looking at our image on their mobile device or a 70-inch display, the images will be just as crisp. Secondly, because they are just a set of instructions, we can create them dynamically based on our data, changing them as the data changes. Finally, all modern web browsers support SVG rendering. In fact, the markup itself is just XML and looks quite similar to HTML. To get started, let's copy our template HTML file to index3.html and open it up in our text editor. We'll just change the title to be all about SVG and add an SVG tag to our content div. Now let's load the page in our browser and see how it looks. Well, the page is empty. But if we open our console and inspect the items, we'll see the SVG tag hiding in the source. We can think of SVG as our canvas or container into which we'll be adding our graphical components. Like HTML, SVG is a markup language with a whole new set of tags to learn. But don't worry, there really aren't that many that get used. The list of elements we'll mostly be using are rect, circle, ellipse, line, G, text, and path. So let's start by drawing a rectangle. Simple enough, just use the rect element nested inside our SVG tag. Refresh our browser and see what happens. Uh-oh, nothing. This is due to the fact that SVG elements require specific attributes to be set in order for the rendering engine to know how to draw them. For our rect element, we'll need to set its x and y attributes, as well as its width and height. Now if we refresh our browser, we'll see a black rectangle in the upper left-hand corner. And this is a good time to mention the coordinate system used by SVG. Anyone familiar with computer image programming will remember that the coordinate system starts at the top left corner at 0, 0. As we move to the right and down, we increase our x and y values positively. So, for instance, if we had initialized our SVG container to have the width of 300 pixels and a height of 100 pixels, we would have a coordinate system that looks like this. Let's also add some boilerplate attributes to our SVG container metadata to help the browser understand which version of the SVG standard we are using. The next element we'll look at is the circle, since there is a gotcha here. If we copied our rect tag and simply replaced rect with circle, we'd expect a circle to be drawn at the same location and with the same dimensions as our rectangle. The problem is that circles do not have a width and height, so we'll need to use a different set of attributes. Cx and Cy take the place of the x and y attributes, denoting the central point location. R is for the radius. Now if we refresh our browser, we'll see our circle. Ellipses work in a similar manner to circles, except instead of supporting a single radian, they require an Rx and Ry for the x radius and y radius, respectively. Finally, if we just want to draw a line, we'll use the x1, y1, x2, y2 attributes to specify the start and end locations. When we refresh now, though, there appears to be a problem. Our page doesn't seem to show our line, even though it does appear in the inspector pane. This is because, similar to the attributes we've already been setting on these SVG elements, there are many others that control the styles of the elements. Here is a list of the main ones we'll use. The missing attribute in our case, for lines, was the stroke attribute. The stroke controls the outline of any shape, but its default value is none, so it naturally wasn't showing up. After setting the line stroke to black, let's refresh our browser and see all of our shapes so far. If stroke can set the line color, let's use it, stroke width, fill, and opacity to jazz up our other SVG elements as well. Now if we refresh our browser, we can see our shapes have some style. Please feel free to take some time to experiment with these attributes. We learned quite a bit here, given our first taste of SVG. Of course, we could have created this quite easily in Illustrator or some other such vector graphics editing program. But now we know how to create these images with code. You may have noticed that we purposefully left out two SVG elements mentioned earlier, text and path. These are a bit more complicated, and we'll take a look at them in the next video, as well as how layering works. In the last video, we introduced many of the basic building blocks to understand basic SVG drawing techniques. In this video, we'll look at some of the more advanced concepts of SVG, such as dealing with text and path elements. We'll also see how SVG elements are ordered or stacked on the page, such as which ones appear on top and which on the bottom. The G, or group element, can help us organize most of our markup. Finally, we'll move some of our styles to a style tag in the page and talk about the pros and cons of using an external style sheet versus defining styles inline. So, let's get started with the text element. Of the SVG tags that we've seen so far, this is the first that uses content within the tag's body. Let's take our index3 HTML page from last time and inside our embedded SVG element, replace the contents with the text element of Hello World. With our server running on localhost, we can test this page in our browser, and there's our text. Now let's enter a longer bit of text spanning a few lines. Loading this in the browser, we see that the text cuts off at the width we specified for our SVG container. Unfortunately, unlike HTML, SVG does not have built-in word wrapping for text elements. So instead, we use the tspan elements to manually add line breaks. You'll notice a new attribute here, dy. The dy attribute indicates a shift along the y-axis on the position of an element, thus creating the look of multiple lines of text. The next advanced SVG element we'll examine is the path element. It wouldn't make much sense for a markup language to only allow circles and rectangles. So, to allow the creation of any custom shape or line, the path element exists. One such example is quite simple, drawing a triangle. The shape of an SVG path element is defined by one attribute, D. This D attribute contains a series of commands and parameters in the SVG path mini-language. Here is a table of the commands used in this language. The case of the command used determines if the x-y position is to be absolute or relative. Let's return to our page to draw a triangle. We use a move-to command, m, to say where we'd like to start. Follow that with two line-tos, L, to draw the next two sides. Then Z will close the path with a line back to our starting point. We'll set a stroke and stroke width so it will be visible where the lines are. A quick reload of the page will show that our triangle works. Let's now make two copies of the triangle and stutter them across the page so that they are visible and not directly one on top of the other. We'll use our fill so we'll know which is which, and then refresh our browser. We now see three overlapping triangles in red, green, and blue. The drawing order of SVG elements is entirely based upon the order they are created on the page. Those elements drawn first will be drawn over by elements drawn later. So to rearrange these triangles, we'd have to move the code blocks used to create them. To move the red one to the front, we'll have to move it down in our code, like so. Now let's say we had some text that went along with each of our rectangles. If we put all our text at the end of the SVG, we'll notice that it appears in an overlapping blob at the topmost layer. Well, that didn't seem to have worked out as we would have liked. Let's instead give a sense that these text elements are held within the triangles. Here is where the G, or group element, comes in. We can group specific elements together to help us organize our code and apply styles in one place. We will add a transform attribute to our group element, which will offset everything within the group the same amount, thus allowing us to not have to edit our cumbersome paths D attribute. Let's take a quick look and, oops, looks like we need to extend the canvas. Let's increase the height to 200 pixels and try again. We see that the triangles overlap without obstructing each other's text. Aesthetically, there are a few problems with our drawing. For one, the text is a bit hard to read, being black on dark colors. The other problem is that the text is a bit too big for our triangles, and it would look better if the text were fully inside the shape. Let's address these problems with some stylistic changes to our text and stroke via CSS styles at the top of our page. Adding these styles to the top of our page really helped the readability of the text in the triangles. The advantage to assigning CSS in the style tag is that we only had to write our styles in one place instead of repeating ourselves for each text element. Thus, with regards to legibility and organization, it makes the most sense to use style sheets for setting styles of SVG elements. The only drawback is that it's a bit of a deal breaker. If you ever plan on allowing users to download your SVGs, or, say for instance, you want to create a server-side function to convert your SVG to a raster image format like JPEG or PNG, all of those styles will need to be in line. In conclusion, we've learned how to draw text and path elements in SVG, as well as how things get ordered. Grouping elements with the G tag helps to alleviate some of the complexities of SVG drawing in the browser. Style sheets applied to SVG elements provides a single point for stylizing multiple elements. The problem with using styles outside of their elements is that it makes such elements harder to share with other applications. In our next video, we're going to apply the knowledge learned here to dynamically create elements using both vanilla JavaScript and D3. Now that we feel comfortable with SVG graphics tags embedded in our HTML page, we'll introduce the concept of using JavaScript to dynamically add SVG elements to the page, much the way we added HTML elements earlier. We'll start with the plain old JavaScript way, then move on to using D3 to perform the same tasks. We'll then finish by adding data to our page to drive the creation of SVG elements. The introduction of data will be a segue into making dynamic data-driven charts with scalar vector graphics. So let's get started. Let's remove the style and content div in our working HTML file to start with a clean slate. The title at the top can be SVG with raw JavaScript. And let's add the same in the H1 header in the body. Then the first thing we want to create is our SVG canvas element. You'll notice here that instead of using the standard document.createElement, we use the more verbose document.createElement NS, with the NS standing for namespace. We need to be explicit in telling the browser that we're not creating regular HTML elements, but instead the SVG element with the XMLNS variable as our first argument and the tag name as the second. We'll also set the width and height of the SVG and then append it to the page. Now if we refresh our browser, we won't see anything on the page. But in the inspector, it reveals the SVG element. Very good. For our next task, let's do something simple, like create a rectangle. Similar to creating the SVG element, we create an svgrect tag with createElementNs, then use the setAttributeNs method for setting the x, y, width, height, and fill properties. Once the element is created and its attributes are set, we append this to our stage, or SVG element. Now refreshing the browser will show a maroon-colored rectangle on our page. We don't even need to inspect anything to see it. Now let's do this exact same task using D3 to show how much easier it makes things for us. We'll use the same syntax as we've done before. Select the body of the page and append an SVG element. We can then chain attribute calls to set multiple attributes. After this, we'll create our maroon rectangle. Here I'm using a different syntax for setting multiple attributes on an element. Some people prefer using this JSON-like style for quickly setting attributes without so many repeated function calls. Reload our page, and our two rectangles are the same. Now let's add some data to the equation. We'll create a simple array of 6 integers from 1 to 6. Note that we could have done this using D3's handy d3.range function, but for simplicity's sake, we'll write out the numbers. Again, we'll create our SVG the same way as above. Next, we'll use our select, data, enter, append technique for adding elements to the page based on the data elements of an array. We used this earlier in our flower example. Now, just to make sure we're on the right track, let's reload the page in the browser and inspect the elements. Yes, the elements do actually exist, even though we cannot see them on our page, since we haven't given the rectangles any visible styles. So our next step is to make our rectangles visible. We'll start with the fill attribute so that we're sure that everything has a color. Next, we need to specify an x and y position. We'll use an exponential function to set our position along the x-axis. This will give the illusion of depth to our squares. The y position can be static, simply half the height. The other means of giving our shapes depth on the page is to have them grow as they come closer to us. We'll accomplish this by using the same exponential function, this time without multiplying by 5. And since these are squares, we need to make them have the same width and height. Now if we refresh the browser, we'll see our squares jump out at us. Well, kind of. It looks like we've moved along very well in this section and are now ready to start creating our dynamic, data-driven charts with D3. We now have a firm understanding of HTML, CSS, raw JavaScript, D3, and now SVG. In the upcoming section, we'll bring all of these skills together to draw basic SVG shapes that are able to update their styles and attributes based on the data passed to them. Stay tuned! Welcome back, and here's where things really start to get fun. In this section, we'll be working with a complex data set and using that to draw SVG elements on a page using D3's enter, update, exit paradigm to build a crude bar chart. For this first video in this section, we'll take a look back at our flower data set from section 2. We'll add a random numerical value to our data set to be mapped to the height of our rectangles. Next, we'll add these elements to our canvas. And in doing so, revisit D3's scale function to make our bars fit on the page. First of all, let's copy our template to index4.html. Let's insert the flowers that we had in section 2 and add 3 more flowers, a rose, a tulip, and a daisy. Just to remind ourselves, we have an array of JSON objects here. This should bring us to a total of 8 JSON objects in our data. We can see that we don't really have any numerical values besides ease of care, but this is more of a categorical value anyway. For the purposes of this video, we'll add a random number to our objects, which will then map to the height of our bars in our bar chart. In order to add this random number, we could go into our data array and simply add a new key manually. But this is a great opportunity to introduce JavaScript's built-in map function, which we can use to iterate through each element, manipulate it in some way, and return our new object. This is a common technique used in many programming languages, especially when dealing with large or complex datasets. We'll pass an anonymous function as an argument to our map function. We'll then assign a random integer between 1 and 100 to be our value key and return this new object. So now that we have the new array of data, let's add it to the canvas in the form of SVG rectangles. Before we write the code to perform this action though, let's think a bit about how D3's inter function actually works. The central utility to the D3 library is binding data to visual elements on the page, be they HTML or SVG. Hence the title, Data-Driven Documents. So when we make a selection using D3 select all and call the data function on the selection, D3 tries to match up the elements of our data array to the elements of our selection. Calling the inter function on the bound data to the selected elements will only return an array of corresponding HTML or SVG elements if there are fewer elements in the selection than the number of elements in our data array. The other way around, that is, fewer data items than selected elements, would cause the exit function to iterate over the excess elements. We'll talk more about that later. This diagram is meant to help us understand the binding between actual data and selected virtual elements in a visual manner. So let's apply this knowledge of how the inter function works to our code and add elements to the page. First, we need our SVG canvas. Let's add it, as usual, to our content div. A width of 500 and height of 300 should be good for our purposes here. Let's make those constants at the top. First, we need to make our selection by selecting all rectangle elements under our SVG element. Since this is an empty selection, meaning that there are not yet any rect elements on the page, and our dataset contains 8 elements, there is a mismatch between the data binding, with more data items than actual elements. So to this selection, we will call the inter to iterate over 8 times, since 8 data items minus 0 elements is 8. Before we overcomplicate things by setting different attributes, let's just append our elements to the SVG, load our page, and inspect the DOM to make sure they are being added. Okay, great! There they are! Now we can go ahead and set our attributes. We'll set our x and y coordinates statically for now. We'll have our bars drawn from the bottom left of our canvas using the height, and our x value will just be 0 for now. As for our height, we would like this to correspond to our new value key in our data. As we've done previously, we'll pass an anonymous function to our height attribute that will return the value of value and set our height. As for the width, we'll also set it to 20 pixels statically. Now, let's refresh the page. Uh-oh, there's nothing there. This makes for a good debugging moment. If we open the inspector and take a look at our rectangles, we'll notice that they're all off the screen. This is because we've set the rectangle's y values to the height of the canvas. When the height attribute is applied, they get drawn down off the bottom of the canvas. So to fix this, let's make our y value the height of the canvas minus the value of the node. Save and reload. Now we see a rectangle on the page. Okay, but why does it look like there's only one bar? Well, if we inspect our elements, we'll see that they're all overlapping each other since we did not specify a dynamic x value. In order to space our bars out a bit more, let's multiply their index value by a factor of 20, the width of our bars, as the x value. Reload and voila! There they are! If we continue to refresh the page, we'll notice that the bars change height. This is because we're assigning a different random value to our height every time. Alright, so most of this video was a refresher course of material we've covered earlier. But it is important that we take a hard second look at how the data and enter functions work to better prepare ourselves for debugging code down the line. In our next video, we'll focus on making some of our attribute values more dynamic and doing a deep dive into D3's scale functions. See you then. Now that we have the basics of a bar chart built, we're going to concentrate on making it more dynamic, meaning that it is less dependent on static variables or statically assigned parameters, such as the width and height of our bars. We're also going to take a look at some of the different scales that are available by D3 to help us map our randomly assigned values to the height and width of the screen. The plan for today will be improving on the previous video's code base by identifying parts of our code that we can make dynamic. After that, we'll spend some time looking at how D3's scale functions work. Looking at our code base from the previous video, we can see that we are setting the width and height of our SVG statically as we've done in the past. Why don't we make this dynamic by detecting the width and height of the user's browser window? To do this, we use the built-in JavaScript properties window.innerHeight and window.innerWidth. Another aspect of our chart that we can make more dynamic is the width of our bars. Currently, we are statically setting them to 20 pixels. But if instead we want our visualization to take up the full width of our browser, we would need to make this a fraction of the page width. So now let's take a look at our visualization in the browser. The bars now stretch across the entire page. Very good. The only remaining problem is that our bars don't reach the top of our visualization. In order to fix this, we'll use one of D3's built-in scales, specifically a linear scale, to map our values to the domain of our window height. Our first step is to get the range of values from our flowers. We'll use D3's built-in extent function, which returns a two-value array of the minimum and maximum values. We'll then feed the result of this into the domain of our D3 linear scale function. Finally, we'll set the range of our scale function to a two-value array from 0 to the window's height. To test the scale we've just written, let's log the domain values to the console. Now let's reload the page and open the console. Does the minimum value of our range map to 0? Does the maximum value map to the height? Okay, everything seems to be working. Now if we use the scale to calculate our y and height attributes, we'll see the resulting bar graph. Looks like we've got it. We can refresh a few times to see how our bar graph changes with the randomly assigned values. We have a completely dynamic bar chart based off of our page's width and height using D3's scale functions. We'll improve on this ever more in the next couple of videos by refactoring our code to handle cases where our data changes and we'd like to update our chart without a full page refresh. Now that we feel comfortable with entering new data items into our canvas and incorporating them in our bar chart visualization, we need to think about what will happen on an update. In this video, we'll extend our flower dataset with a few additional items and dynamically update our visualization based on the new data stream. This will fully utilize the D3 paradigm of creating a data-driven document. So let's take a look at today's game plan. We'll first refactor our code and create an update function that will take new data as an argument and subsequently update the visualization. We will then write a function that we can call from the console to add a new item to our data set for testing our update function. We'll show the difference between entering and updating elements and show how to distinguish between the two with style. Let's start by writing our update function. We'll just wrap all of the drawing code for the rectangles, not the SVG, into a function called update, which will take new data as its sole argument. We will also need to reorganize some of our variable initialization since we'll need to recalculate our scale and bar width every time there is a new data added. Each instance of the variable flowers needs to be changed to new data within this function, since that's what our argument is now called. Don't forget to call the function at the end with flowers to invoke the update. Finally, just to make sure it is still working, let's save what we have so far and refresh our browser. Okay, it still works. Now let's see what happens when we add new data. We can test this in our console by appending a new flower to our flowers array. Here, I'll just make up a test flower. It seems that when we try to call the update function, we're getting an error that we cannot set our attribute to nan. That's JavaScript speak for not a number. Taking a closer look at our code, we'll notice that we are giving our flowers a value outside of our update function. This is why our new flower is not getting a value set, and thus is unable to set our rectangle's y and height attributes. So let's move this code fragment into our update function. The only problem is that we don't want to override our previous values if they've already been set. So we'll check if the flower has a value, and if not, we'll assign it one. Now if we refresh our browser and try our console commands again, we'll see at least now we're not getting an error. But we're still not seeing a new bar appear either. What's going on? We can continue to add new elements and call our update function. But no matter what it seems like, the page isn't showing our new bars. And what's even more confusing is that when we run D3 select all rect in the console, we see that the number of rectangles on the page is increasing. Looks like we need to go back into our code and try and figure out this problem. The reason that this is happening is because we are only applying attributes to these rectangles on enter. We need to instead apply those attributes on both enter and update. So let's refactor our code a bit and see what happens. We'll separate out our enter code to only append the rectangles on the page. After that, we set the x, y, width, and height attributes for both the newly entered elements and the elements carrying over from the previous call to update. So as to more easily see new rectangles, let's also set the fill of the rectangles to black when updating and green when entering. We now have a pretty robust bar chart that can accept new data and visually show changes. The only thing left, which we'll do in the next video, is to show how to exit elements from the canvas and give our bars labels and padding. Okay, we're back and ready to complete our bar chart. By the end of this video, we'll have a complete bar graph that can accept variable length data with labels. For today's game plan, we'll start by adding padding between our bars, a subtle aesthetic change that will make a huge difference. Next, we'll add labels to show the actual value of the bar we're seeing. And finally, we'll add an exit function to remove bars when the data fed to our update function decreases in size. Starting with the padding, we'll make a variable called padding at the top of our script. In order for this to be dynamic, we'll make this a percentage of the page's width. Let's try 1% to start with. Now we'll need to subtract this from our rectangle's width. If we refresh our browser, we can now see a much more legible chart with our 1% buffer. Our next task is to create labels. Having a visual representation of our data does not suffice when the user may be interested in learning the actual numeric value that they are looking at. For this reason, it's important to add labels. You'll notice that this looks similar to our rectangle code. Now if we test in the console, we won't actually be able to see anything, but we can test that our labels do now exist. The next step is, in our update phase, assigning each text element its text and styles. We'll obviously set the text to return the value we would like to display. For the x attribute, we'll use the same math we use for the bars. And for the y attribute, we'll just set this to the height of the page so that it's at the bottom of each bar. Save that and reload the page. You'll notice we can now just barely see the text at the very bottom of the page, peeking up. This is because we need to subtract the size of our font for it to be baselined at the bottom of our page. We'll also explicitly set the font size, and text anchor. Reload and see what we get. We're starting to get there. We just need to center our text with our X attribute. We'll want our X attribute to be our current index times our bar width plus half of our bar width minus our padding. Save that, reload, and voila! We now have centered labels. Our final task here is exiting bars that no longer exist in our data array when we call update. If we test updating our bar chart in the console after removing a data point, we'll discover a bit of a problem. Luckily, D3 has an extremely easy way to help us handle this. The exit function works very similar to enter in that it contains the selection of elements on the page which no longer exist after the new data has been bound. Remove on exit for both rects and texts. Reload the page, and now, if we test popping items from our bar chart, we'll see that it updates properly. This is great! We've now built our first dynamic data-driven visualization. Granted, it's only a bar chart so far, but we've laid the groundwork for implementing much more complex charts and visualizations. In the next section, we'll look at how we can bring the data from an external source to build a scatter chart. One of the most beneficial reasons for using visualizations is to be able to discover answers to questions much faster than using data alone. How does this happen? As humans, we devote a large amount of our cognitive ability toward pattern recognition, so we are often able to spot trends visually much faster than we can from viewing data in a spreadsheet or database. Thus, in Section 5, we will be building a scatter plot to answer the question of which countries are growing the fastest in terms of exports. In this video, we will be using trade data from the Observatory of Economic Complexity via their Open API. This will be a great exercise in getting to know how to use external data sources from public resources. For our game plan in this video, we'll start by looking at the Observatory of Economic Complexity's API to learn how to query their dataset. We'll learn the structure of the data calls and test them in our browser to make sure they work and are fetching the data we need. We'll then look at the D3 documentation for loading external resources via XHR methods. XHR requests do not require a full page refresh and instead load data in the background. Finally, we'll put all of this together and begin writing our scatterplot code by fetching the data for 2010 and 2011 exports by country and formatting them into a keyed object to feed into our scatterplot in the next video. So let's get started by looking at MIT's Atlas Media site. We'll see a search box on the home page, and if we navigate to the About section, we'll see a link for the API. Let's click that. We can now see that there are two different ways we can use this API, either to embed a visualization or to query for the data itself, which is what we'll be doing. So let's click on the Data link. Looking at the documentation, we can see that the basic call structure of the API requires us to specify the following variables: classification, trade flow, year, origin, destination, and product. Reading the documentation further, we can learn what values can be used for each of the variables. Classification can be one of SITC or HS, which are simply two different product classifications. Trade flow can be either export or import. The year can be any year between 1962 and 2012 for the SITC classification of data, or 1995 and 2012 for the HS classification. Origin and destination are both three-letter country codes which can be found by using the search box. Product is a 4-digit product code for either SITC or HS products, also searchable on the site. Scrolling down, we can see examples of different data calls and what they return. There are two other keywords we can use for some of the variables, show and all. For example, if we look at the first example for querying for total trade by country, we see that the example URL structure is a classification of HS. Trade flow is export. The year is 2010. Origin is show. Destination is set to all. And product is all. In English, this URL would say, we would like to view or show all export data from origin countries in the HS classification. The all keyword specifies that we are not specifying the variables destination and product, so we want it to return all individual values. Now if we copy and paste this URL into our browser, we can see the results of the data query. It appears that there is an object with one key, data, that contains a list of every country and their export amount, as well as some other information that we're currently not really interested in using. One thing you may notice that we're missing are the names of these countries. All we have are the database IDs used for them. Scrolling up a little bit in the API documentation, you'll find a section called Attribute Lookups. We can use these API calls to get the names and other detailed data about both countries and products. So now that we know how the observatory's API works, we'll need to figure out how to request this data from our application. We do this through what is called an XHR request in JavaScript. The XHR request is how we make background data requests to external resources. Luckily, D3 has a great interface that takes a lot of the heavy lifting off our shoulders. If we pull up the D3 documentation, we can see the different methods we could use for this. There are many different methods that enable the user to request specific data type resources. For example, there is D3.csv, which is tailored to accept comma-separated value data and format it appropriately. There is also the D3.json method, which we will be using for the request of JSON data from the observatory. These methods are all shorthand for the more generic D3.xhr method, which can be customized to perform more specific tasks. Now that we're somewhat familiar with how the D3.xhr API works, and we know which data calls we'll need to make, let's get to writing our application. We'll start once again with the basic HTML5 template page. Copy template.html to index5.html, and let's work with this file. We'll write a very similar code block to the sampled D3.json code. In fact, let's just copy and paste that from the D3 documentation. We'll just need to change the URL to the one we tested earlier. If we run this in our browser and open our console, we should see the following. We can explore this data and learn about its structure and see how we can use it for our scatterplot. Since we'll be comparing 2 years' worth of data, we really need to make 2 separate JSON XHR calls. So let's embed a second call within the first. We also want to merge these 2 datasets. The easiest way to do this would be to create a keyed object with the IDs of our countries, or origin _ ID. So first we'll initialize our global data variable to an object. We'll then loop through our 2010 data and create new objects for each item in the array with the origin ID for the key. This object will then contain a 2010 export value and the origin ID within it. Then we can do the same for our 2011 data, but instead of creating a new object, we can test if one already exists and add its 2011 export value if it does. If it does not exist, we do not want to create a new object, because our scatterplot will only be able to show items that have both 2010 and 2011 export values to align with the X and Y axes respectively. Now if we test this in the browser, we'll see our new keyed object with data from 2010 and 2011 as well as its ID. Well, that was fun. Now that we have our data, we can finally begin drawing our scatterplot. This is what we'll be doing in our next video. Now that we've gathered our data from the API and formatted it in a way that we like, we can begin drawing our scatter plot. By the completion of this video, we'll have a scatter plot showing 2010 export values on one axis and 2011s on the other. The graph will be mostly complete, save the axes labels themselves. We will start by drawing our circles on our canvas using SVG circles entered to the canvas. We'll continue by applying a scale so that they all fit on the page. Next, we'll take another look at the API to learn how to fetch metadata about our countries, those IDs we have but with no names. Finally, we'll conclude by debugging any errors that may arise. We should start by initializing our width, height, and SVG canvas at the top of our script, right after declaring the global data variable. Once we have a canvas to write to, we can add our circles to the canvas. Recall from the last video that our data is an object keyed by each country's ID, so we'd need to initialize our circle's data through the D3.values function, which returns an array of objects. Each object within our array has 3 keys: export val 2010, export val 2011, and ID. We'll decide, somewhat arbitrarily, to use the 2010 value as the x-axis and the 2011 value for the y-axis. We'll need to make sure we write our code nested within our second D3 JSON call, so that we can be sure that both data calls have completed before we start drawing. We'll use a static size of 5 pixels for our radius, since we are not attaching any meaning to the circle's size. Loading the page in the browser, there aren't any circles. If we inspect our elements, we'll find that the values we set for CX and CY attributes are much too large to fit on our screen. This looks like a job for a scale. Oh, and the page title bothers me. Let's quickly set that to yearly exports in the header and just remove it from the body. With that distraction out of the way, let's now create our scale globally at the top of our script. The range is simply from 0 to the width and height for the X and Y scale respectively. The domain needs to be set once both data calls have been completed, so we set it for the respective axes after our console log call and before drawing our circle. Then we need to set our CX and CY values to their respective scaled values. Now if we refresh our page, we can at least see some circles. Yay! But that just doesn't look right. Our Y values are starting in the upper left-hand corner when the convention of a normal XY plot is to use the lower left-hand corner as the origin. This is actually an extremely simple fix using scales. All we need to do is reverse the order of the values we are passing to our Y scale range. Now the incoming minimal domain value will be mapped to the bottom, or height, of the page, and the maximum domain value will be mapped to the top. Reload the page, and everything looks good. There's one other data call that we glanced over in the Observatories API in the last video, the metadata for these nodes. Specifically, how do we know which country or product is which? It would be nice to have their names, and maybe some sort of color scheme to differentiate them. If we browse the API documentation once again, we'll find that there is a section devoted to attribute data calls to retrieve metadata. So we can use this call for countries and apply the resulting data to our circles. First, let's take a look at the country attributes data call in our browser to see what values are available. How delightful! Both names and colors are available. For now, we won't worry too much about the names of the countries, though we will be using them later. Let's just initialize the new global variable country attributes at the top. Then, before fetching the import data, let's fetch the countries. If there is an error, output it to the console as a warning. Then go through each item in the country's data array and assign the relevant country attributes to the country ID. Where we plot our circle, let's set the color, which the API documentation notes conveys the continent of the country as the circle's fill color. Now when we reload the page, we get a variety of colors. We have now added a new layer of data to our chart. However, you may have noticed that we are getting an error in our console. NaN again. What could be causing this? Well, it looks like our CY attribute is sometimes being set to not a number, and our CX attribute is always okay. This suggests that there is an issue with our 2011 export values, since this is where we're setting the y-axis. If we put in a console log statement where we're setting our CY attribute, we should be able to figure out the issue. Now when we run our script, we can scroll through our console statements and view the data that's causing this issue. Aha! We found one. It appears that some of the countries do not have 2011 export values at all. Thus, we're unable to set its CY attribute. Let's add a test for this edge case so that this error won't come up again. We'll want to be sure that each datum has a 2011 export value, and if not, set it to the minimum of the range. Such a test isn't necessary for 2010, as that's always gathered in the outer loop. Reload the page and no more errors! Now we've created our scatterplot using data fetched from an open API and drawn on our page. In the next video, we'll figure out how to set axes with labels and a key, as well as experimenting with using a logarithmic scale instead of the linear. This is our final video for section 5. Here we'll be concentrating on the last but most important part of a scatterplot, the axes. Luckily, D3 has great built-in support for adding axes to our charts, although there are still some caveats that we should be aware of, which we'll go over. As for our game plan, we'll first spend some time looking at the official D3 documentation for the axes component, as this will be helpful once we start coding them. Next, we'll implement a rudimentary x-axis. We'll then add some default styles to make it a bit more pleasing design-wise. After that, we'll show how easy it is to reuse the same code for our y-axis. We'll then convert our linear scale to logarithmic and see what the implications are on our chart. Also, we'll need to do a bit more formatting to make our scatterplot look the way we'd like. Finally, let's add some text labels to our circles and group them via SVG G tags or groups. So let's dive right in and take a look at the D3 axes documentation. The first thing we'll see are some examples of different types of axes with source code provided. If we scroll down, we'll see the different methods supported. The general code structure for using axes is to create them with whatever methods we may want configured and then apply them via the call function to a D3 selection, usually a G element. We can see an example here, and as it says at the top of the page, the axis component is designed to work with D3's quantitative, time, and ordinal scales, which is perfect, seeing that we're already using a linear scale to get the proper XY values for our scatterplot. Without configuring anything special, this is the absolute basic code we'll need to create and draw an axis on our chart. All right, here it is. It doesn't look very pretty, does it? First of all, we'll want to add some styling to reduce some of the visual clutter. Then we'll want to abbreviate our numbers somehow. Finally, we'll want to move our x-axis to the bottom of our chart. Let's take this one task at a time and add some styles. Starting out, we're removing the browser's built-in margin. Next, we'll be replacing the thick black bar along the axis with a thin black stroke. And finally, we'll want to set the text to use a sans serif font family and reduce its size to 11 pixels. Reload the page, and already it looks so much better. Next, to specify a number formatting, we can use the tick format method on our axis function. If we run each value through a D3 number formatter function, we can have something a little easier on the eyes. One slight caveat with using the S, or scientific formatting, is that the billion unit values have a G for giga suffix, so we can just replace that with a B for billions. Reload the page, and yes, it's a hack, but it works! We'd also like to move our axis to the bottom of the page. We can accomplish this quite easily using an SVG transform on the G group element. Also, since we're moving the axis to the bottom of the page, we'll want the values of our axis above it. For that, we'll specify the orient to be on top. After a reload, our chart is starting to look a little better. Now let's copy this code we just wrote for our y-axis. Two changes we'll need to make are, first, we need to set our orientation variable to the right instead of the top, so that our values will be on the right-hand side of our axis. And secondly, that we do not need to transform the position of our axis to the bottom of the canvas. Reload the page, and it's really starting to look great. Of course, if we take a close look at our chart, we notice that most of the circles are bunched up toward the bottom left, and that there is just one country in the very top right corner throwing off our distribution. This seems like a perfect case for using a logarithmic scale. So let's simply change our scale from D3 scale linear to D3 scale log and see what happens. The circles themselves definitely look more spread out, but now the ticks on the axis are completely illegible. Since D3 defaults to use log base 10, it would be great if our chart would only show powers of 10 values and format the numbers properly with 10 to the specified power. Luckily, the D3 axis function gives us access to how the tick values are formatted via the ticks function. Since this is a common task, or at least one that has come up before, we can look at a nice example that Mike Bostock has created here. Since the entire D3 library is open source, and the community is very active and helpful, there is no shame in reusing someone else's code. This code does exactly what we need and is written succinctly. So let's copy and paste the fragments into our chart. But let's also try to dissect this code a bit to understand what's going on before we blindly adapt it into our project. First, we have a string with superscript numbers. Next is a function called formatPower, which will take a number, coerce it into a string, and return the superscript of it. Now if we look at the ticks function, which we are now using instead of tick format, we'll notice the first argument, 10. If we look at the D3 documentation for the ticks function for log scales, it says the number of ticks cannot be customized due to the nature of log scales. However, you can filter the returned array of values if you want to reduce the number of ticks. So, we are filtering which ticks will be shown and also passing as the second argument the formatter function. This will concatenate the number 10 with the superscript of which power is currently being displayed. So now if we refresh our page, we have a beautiful logarithmic scatterplot with powers of 10 for labels. The last item on our agenda today is to look into adding a text layer to our scatterplot and grouping them together with our circles. We can do that by refactoring our code just a little bit. Instead of appending circles on enter, we'll enter with SVG group elements and append both circles and text to them. For the most part, we're essentially copying our code for creating our circles and changing our CX and CY attributes to just X and Y. We'll also want to add a text element to output the display ID. Finally, similar to the check we put in for our export 2011 values, we'll also want to be sure this display ID exists before we return it to the text method. Let's take a quick look to see what it looks like. Not bad. But, as an exercise in design, let's see how our chart looks without our circles altogether. This way our labels act as our points on the chart. You know, I kind of like this better. We've now completed section 5, building a scatterplot. We worked with an open API and learned about the D3 axis component along with how to customize it. In the next section, we'll focus on adding interactivity to our chart and exploring what new UI hurdles this puts in our path. Welcome to section 6 of the Building Interactive Data Visualizations with D3.js course. This section will be all about the interactive part. So far, our visualizations have not been very dynamic, meaning that once we've built them, that's pretty much all the user sees. Now we're going to be leveraging the most useful part about having the SVG visualizations on the web, which is that they can listen for user events such as clicking or hovering as easily as any HTML elements. In this section, we'll be working with our scatterplot from the previous section and adding the ability to change data and manipulate the chart in a number of ways using D3's event model. This will then lead us into section 7, in which we'll transform these basic updates to our chart into beautiful animated transitions. The first video in this section will be a very simple introduction to what events are and how they're handled by D3. We'll finish by attaching a click event to a button that will then toggle the visibility of our chart's labels. Let's start by copying our index5.html file from the previous section to index6.html. Once copied, we can uncomment the circle code. Once that's done, save the file and pull it up in the browser to be sure everything still works. Circles and labels are both there. Everything looks good. Now I think we are ready to register our first event. Let's create a button in our HTML page, select it with D3, and register an event that will simply output that it has been clicked to the console, so that we know we did it properly. Now if we refresh the browser, pull up our console, and click on our button, we'll see the message in our console. Perfect! Now let's try to do something a bit more useful. Our original intent was to toggle our labels' visibility. Let's start by adding code to hide our labels. Also, let's change the text of our button to say Hide Labels. The code we'll use to hide our labels will simply change the text element's display style to none. Now viewing this in the browser, we see that when we click the button, the labels will disappear. But if we click a second time, the labels remain hidden. We need some logic to determine the current state of the label's visibility and change whether we show or hide the labels based on this variable. Recall that if we call a style or attribute method on a selection without passing a second argument, the function will act as a getter and return the current set value. So we can select the country's first text style and store this in a variable to use as our logic gate for whether to show or hide our labels. Now refreshing our browser, we see that we can both show and hide our labels by clicking the same button. Yay! There is one minor problem left. From a UI perspective, it would be much more helpful if our button's text also changed to say Show Labels when they are hidden and Hide Labels when they are visible. This is a simple enough fix. We'll just always set the text to our button to what it should say. In the D3 documentation, one of the things noted was that the this context within a listener event is always the current element. We can use this to our advantage and simply select this instead of reselecting the button. After reloading the page, we have our beautiful chart with a button to toggle the visibility of our labels, with the button updating based on the current state of visibility. In the next video, we'll look at how we can actually change our data and thus manipulate the elements in the chart itself. Now that we're a bit more familiar with how D3's event model works, we'll attach a hover event to our circles to show the actual values that they represent with a tooltip. This will serve the purpose of removing some of the visual clutter from our scatterplot, such as the labels, and show us some other common interactive techniques for charts and visualizations. Showing information on hover is a great way of hiding irrelevant data until the user is interested in it. It is also known in the InfoVis world as Details on Demand. We're going to start by attaching a hover event handler to our circles, similar to the technique for setting a click handler on our button from the last video. We'll then design a really slick tooltip with dummy data to get our HTML and CSS in order. Then we'll connect the two and have our hover listener update the tooltip. Finally, we'll use the user's X and Y coordinates from the mouse position to determine where to display the tooltip. Starting out with our code from the last video, we'll take the liberty of deleting our button and button click code. It's not that this was all for nothing, but you can think of it as the appetizer for the main course. We'll also delete all of our text elements since we'll now be showing this data in our tooltip. So now that we've deleted this extraneous code, we can attach our event listener right where we created the circles. Instead of using click as our event type, we'll use mouse over. To help us see what data is given to this listener function, we'll console our parameters, including this, to our browser log. Now if we run this in the browser and mouse over a circle, we'll see our console statements show up. It may seem tedious to continually write code and run it in the browser, but it's much easier to test JavaScript piecemeal as you're writing it to find minor bugs along the way, instead of after you've written 100 lines of code and may have multiple bugs scattered throughout. Our next task is to design our tooltip with HTML and CSS. Since this is a D3 JavaScript course, I'll spare you some of the details of this somewhat arduous process. But it is still good to know how to prototype visual elements before trying to hook them up with your interactive visualization. The idea I have in my head for a tooltip would be to include the title of the country with its 3-letter abbreviation and continent, that is, its metadata, along with the values of both years' worth of data that are being shown on the X and Y axes. In HTML, that would look something like this. If we view it in the browser, it looks pretty basic, but at least we know we have something to work with. By using fictional values, we can begin to prototype our design. Now let's add some style to make this look a little better. The most important line here would be position absolute, so that our tooltip doesn't push down our chart. Now if we refresh the browser, we'll see something a bit more pleasing to the eye. Our next step is to connect our hover handler with the tooltip to update our display with the focused elements data. This should be a fairly straightforward task, since we have hooks to access all of our tooltip elements. We set the country name, abbreviation, and continent without much formatting. The only special thing to note is that the country's continent is not an attribute of the country's metadata, but instead something we need to get from the country attributes lookup. Every country ID begins with 2 characters that can be used as the lookup for the country's continent. Let's test this much in the browser. The country, its code, and region are all updated. Very nice! To complete our tooltip so that it's fully updated with all of the data available, we need to add our 2010 and 2011 values. One thing we need to remember is that some nodes do not have 2011 values, so we should check to make sure that they exist before outputting them. We will also need to create a format function for our values so that they are displayed with commas and a $sign. This is easy enough using D3's format function. Now if we refresh our page, we can see our tooltip updating with new data in action. The last thing we need to do here is have our tooltip show up where the cursor is. The selection on documentation in D3 mentions that an event is not passed to our listener, but we should instead use the global D3 event variable. Well, let's print the D3 event to the console to see what it contains. It is clear that there is quite a bit of interesting data in here. The relevant lines to us are the page X and page Y variables, as those are the coordinates of the mouse at the time the event was triggered. Since we now know where the mouse is, it's a simple matter to set the left and top styles of our tooltip so that the tooltip is placed at the location of our mouse. If we view this in the browser, there are 2 problems that will immediately stand out. First, the tooltip doesn't disappear when we move off of a node. And second, the circles that are close to the right side or bottom of the browser end up getting cut off. We can solve the first of these issues easily by adding a mouse out event handler that will simply hide our tooltip. We will also need to explicitly make the tooltip visible when we mouse over now. And we might as well set the initial display property to none in our CSS so that when the page is loaded, the tooltip is hidden. The second problem will take a bit more work to get right. The best approach would be to see if the tooltip is off the page, either to the right or the bottom. And if so, shift the origin away from that edge. Starting with the left property, we can see if the width of our tooltip plus the mouse's X property is larger than the width of the page. If so, we'll set the left property to be the current mouse X position minus the width of the tooltip. We can use essentially the same logic to shift the top property up when we're off the bottom of the page. Now if we mouse around our chart, it's impossible for the tooltip to go off the page. Aha! We've won! Now we have a robust tooltip for our scatterplot that has enabled us to reduce the visual clutter of our chart. Furthermore, it allows us to show the actual details of the values being shown so that someone interested in doing analysis using this tool, which is the goal of any visualization, would be able to do so. Coming up in the next video, we'll start adding user interaction. The final two videos in this section will be very closely related and will involve the completion of a single task of allowing the user to specify which year's data they'd like to view. This first video will focus on getting our page set up with the form elements required to capture user-submitted data and refactoring our JavaScript code to be more modular. The final video in this section will focus on adding our drawing code back using the enter-update-exit paradigm. In this video, we will distill our code down to its basics and re-implement what we've done so far in a way that is more conducive to updating data via an HTML form. We'll start by designing the visual elements of the form with HTML and CSS. After that, we'll use D3 to listen for the form submission events and determine which year's data has been requested. Finally, we'll refactor the JavaScript to generalize some of our hard-coded values to be more generic and thus more modular. So let's start with our page from the previous video and comment out our JavaScript so that we can start fresh and just focus on the HTML and CSS of our page. Before our tooltip HTML, we'll add a div with the ID of viz as a placeholder for our visualization. Below this, we'll create a secondary header to denote where the page controls will be. Here we'll add an HTML form element, inside of which we'll add all of our input elements. Let's start with the x-axis dropdown. Since the OEC has data from 1995 to 2012, we'll create a dropdown with an option for each of these values. Since our y-axis could also be set to any of these values, we'll simply copy and paste this drop-down and change the ID to y-axis. Below this, we'll have a checkbox for whether or not we want to show the labels of our nodes. Finally, we can't forget the Submit button. We now have all the elements we need in the page, but let's see how it looks in the browser. As you may have suspected, without any styles, the page looks fairly bland and even a bit confusing. We'll start by organizing the styles at the top of the page a bit. With the auto margin, we'll center the contents of the page within the width of 800 pixels. We'll also surround the viz with a border and assign it the height of 400 pixels. The border is just to remind us where it will go while we're designing. Finally, we'll tell our input and labels to have a display of block with a top padding of 10 pixels to give them some space to breathe. As I mentioned before, this is not a course on CSS or design, so we'll try to keep our aesthetic changes to a bare minimum and focus on the visualizations. Now if we refresh the browser, we'll see something a bit more pleasing to the eyes. Now that we have our form, we'll want to be able to listen for when the user submits a change. Using D3, this works in the same manner as how we listen to a click or hover event. We'll select the form and using the on method, pass submit as the type. We continue with the anonymous function, which will be the callback function for when the form is submitted. By default, submitting a form via HTML causes a full page refresh. So we'll want to use the prevent default method on our event to prevent that. Let's also send some text to the console so we know that it worked. Now we can try this in the browser. And there's the response without a refresh. Looking good. The next and final task for this video is to refactor our JavaScript in a way that is conducive to fetching data potentially multiple times and updating the visualization accordingly. Leaving our drawing code aside for the moment, we'll write some boilerplate code for how we'd like the logic to work. Starting in our form submission listener, let's use placeholder variables for the x-axis year, y-axis year, and show labels checkbox. Next, we'll pass these variables to a function that will fetch the data we need. In our fetch data function, we will need to potentially fetch the country attributes, if they have not already been loaded, and fetch JSON data from the API independently for each year. By indenting these lines, we are reminding ourselves that each of these variables will be set in the callback function of the previous API call. Finally, we'll call a third function to update our visualization with our new data. Now for our update function, we'll make some notes about the order of processes we'd like to write. First, we'll figure out which year's data we have by inspecting our JSON data. We'll need to merge both years' data into a single array of data. Next, we'll calculate new x and y scales based on the extent of our data values and update our axes. After that, we'll enter, update, and exit our circles. Finally, we'll need to either show or hide our labels depending on what the user requested. In the next video, we'll write the actual code for these functions, reusing as much as we can from the second video of this section. In this final video of the section, we'll complete our user updated scatterplot. In the previous video, we refactored our code so that we could begin reinserting chunks in a more modular manner to allow for updating without a page refresh. In this video, we'll be coding the placeholders that we left as comments in the last video. We'll start by having the user select years from the drop-down menus and fetch the data via the API for our corresponding years. We'll then merge these two datasets into one large array. After that, we'll actually update the visual elements of the page, the circles. Since our data structure has changed, we'll also need to update our mouseover code to be more generic and allow for displaying any values from the x or y axis. Finally, we'll determine whether we need to show or hide our labels. Looking back at where we started our refactoring from the last video, we see that our first task is to determine the years the user selected from the pull-down list. This is one task that plain vanilla JavaScript is actually best at. We can select our respective element by its ID and use the .value accessor to find which year is selected. The only difference for our checkbox is that we use .checked. To make sure this worked, let's log the currently selected values to the console. We can change the values and submit multiple times to be sure that our code is working well. And it looks like it is working well. Now, passing these values to our fetch data function will reuse some of our code from the second video. First, we need to add our country attribute lookup data call. As the comment suggests, check to see if the data exists or not, and only fetch it if it doesn't. Oh, and our data and country attributes objects exist globally, so don't forget to initialize them at the top as well. Next, we'll want to replace our hard-coded year values with the values submitted by the user. We'll omit bringing over the data merging code for now, in favor of just testing that the data is fetched. Finally, as a sanity check, let's once again output our data to the console to make sure everything is working. Load the page up in the browser, select some years, and submit. Looking through the log, it appears to work. Excellent! Before we can move on to our update function, we need to initialize our global variables, axes, and SVG element. Remember that we want our SVG to live in an 800 by 400 div, now with the ID of viz instead of content. A padding of 20 pixels would also be a nice thing to add as a global variable and as a margin style to the SVG. If we reload and inspect our page, we'll see that our SVG element now resides with a nice padding inside our red rectangle. Next, we'll move on to implementing our update function. The first thing we need to do is determine the years for the X and Y axes. The year is returned within the API return values, so we'll get the year from the respective first items. Next, we'll gather our data by processing the two JSON arrays for each respective year, inserting the values into the data object. Once gathered, we can test this in our browser by logging our data to the console every time it is changed and inspecting it. It might also be a good idea to comment out the previous console log calls to reduce clutter in the output. Now let's select a couple of years, submit, and have a look at the data. That's it. Looks good. So now let's deal with the axes. First, append the group elements for the axes after the SVG has been initialized. We just want to do this one time, which is why it's in the initialization code. Remember that we need to shift the x-axis down by the height to put it at the bottom using the transform attribute. For both axes, we want to add the IDs of x-axis and y-axis respectively to draw and update them later. By later, I mean after the data has been completely gathered in our update function. First, update the x and y scale domains, then draw the respective axes. For testing purposes, we can refresh our page and submit the form to see our axes draw and update. It works! We should be familiar with the next part from previous videos, entering, updating, and exiting our nodes. Let's start by selecting all of the g.country elements and assigning the data to enter our new nodes. We'll then create a variable just for the enter phase, appending the G group with a class of country. Using the variable holding the newly entered G elements, append a circle and text. For the update phase, select the circle from country G and paste in everything remaining from the CX attribute down to the mouse out handler. It is important not to use select all with this, as that would be setting up a virtual selection rather than an actual selection of the elements, and not update the data for all children of G with class of country. Don't forget to put in an exit function to remove nodes that may not exist once the data is updated. If we refresh our browser and submit our form, we'll now see our beautiful chart updated with specified years. Oops, but there is a problem. Our tooltips are still hard-coded to show 2010 and 2011 as titles, and the data isn't updating properly, unless of course we selected 2010 and 2011 as our axes to display. We need to update our mouseover function to set these titles to their proper year. Let's first wrap our year with a span tag and a class of year so that we can easily target it for updating. We'll also change the ID of our table rows to val_x and val_y respectively instead of with a hard-coded year. Now we can go into the mouseover code and set the specified year in the title as well as the value. Reloading the page and looking at the effects of the changes in our browser, we'll see that not only have the values changed, but so have the titles. They now say 2000 and 2005, or whatever it may have been that you cared to select. The very last item on today's game plan is to either show or hide the labels, depending on if the checkbox was checked or not when the user submitted the form. This, again, will require us to mostly copy and paste in code we've already written. We'll just want to wrap this in an if statement, testing whether or not to show the labels. Other than making sure that our y-axis key exists, the main functionality we need to add is to explicitly set the display style to block in the case that the labels are to be shown, or none otherwise. Reloading our page in the browser, And we now have a fully functional chart, complete with user interaction from submitted data. We've made great strides in this section, starting with a static hard-coded idea and coming to a fully interactive chart is a huge leap. We'll continue on with this example in the next section with a focus on adding animation to show how nodes are being updated. In this section, we're going to explore the wonderful world of transitions with D3. Transitions, or specifically animations, in a visualization can be extremely impactful and helpful to the viewer if used appropriately. Since the human eye is trained to notice and track movement, adding transitions to a graph or chart can be a great way to focus a user's attention on a specific change or data point. D3 makes transitions to our visualizations relatively painless. But, as with anything, there are a few gotchas to watch out for. In this first video, we'll start slowly by just covering the basics of creating transitions and tweaking different parameters to explore the subject. Once we've mastered the basics, we'll incorporate what we've learned into our previous scatterplot visualization to round out this section. For today's game plan, we're going to look at how to change a transition using duration, delay, and ease. We'll also explore some idiosyncrasies, such as chaining one transition after another, as well as transitioning from one shape to another. We'll then conclude by doing a fade-out transition and removing an element from the canvas. So let's get started with our basic template that we can use as our background for experimenting with transitions. To the HTML part, let's just set the title to Playing with Transitions and add a div with ID of canvas for our SVG canvas. In the main script, let's just add a simple shape, say a rectangle, to our canvas to use as our guinea pig. Save that and load it in the browser just to make sure we haven't forgotten the basics. Now, in order to trigger our transition, we'll need some event to fire that we can listen for. Since we're already familiar with buttons and on-click events, let's use that. First, we need to add our button to the HTML. After that, the simplest transition we can do is to alter one of the attributes of our red rectangle. So let's create a callback function for when the button is clicked. In the click handler, change the X value to 400 on our rectangle. Reload the page, then click the button to see what happens. The rectangle jumps 400 pixels to the right. Now let's call the transition method in between where we select our element and change its X attribute. Reload and hit the transition button to see this in action. Did you see the square run across the page instead of jump there? So, what D3 is doing under the hood is interpolating the X attribute values over a period of time. The default here happens to be 250 milliseconds, or a quarter of a second. If we refresh the page, then look in our inspector and highlight our rectangle, then click our transition button, we can see the X values quickly update. Don't blink or you might miss the changes. As I mentioned, the default duration for an animation is 250 milliseconds, but we can easily change that with the duration method. So let's try changing this to 1 second or 1000 milliseconds and view the results in the browser. The changes in the X value are now a bit easier to watch go by. We can also add a delay to our animation. Say we want to wait for a second before our animation starts. This is also just another method with the name of, you guessed it, delay. If we test this in the browser, the square doesn't start moving until a second after the button was clicked. The final aspect of a transition that will change is the easing, which describes the path or timing of the transition. You can think of it as a predetermined animation pattern. If we look at the transition documentation on the D3 wiki, we can see that we have a lot of choices for easing. So let's change this to elastic using the ease method in our transition. Like the previous two methods, delay and duration, the ease method is set with a default value. The default duration is 250 milliseconds, with the default delay being 0. Similarly, the default easing is cubic in-out, which speeds up and slows down the movement from 0 to 400 pixels. So let's refresh our browser and see our elastically moving cube in action. Hey, that was neat! The square went past the 400 pixel point, then bounced back and forth around 400 before settling into place. It's as though it were tethered to the location with an elastic band. So, now that we're getting a bit more comfortable with our transitions, let's say we want to transition our red square to green after it had moved. Here is where things begin to get a bit more complicated. If we simply add this method chained to our previous code, refresh our browser, and hit the button, we'll notice that both transitions happen at the same time. That's not exactly what we were going for. A naive implementation of this would be to utilize the delay method and add two transitions on the same object. We can test this, and it will work. But this is not the most elegant solution, as it requires us to predict how long the previous transition takes. Imagine we have 5 animations in a row, all with different durations. Now things start to become a bit more complicated. A better way of doing this is to take advantage of D3's each function and listen for the end event of our transition. Every transition has both a start and an end event, which are fired at the beginning and the end of the transition. We can listen for these and use them to call whatever code we want, including another transition. Hooray! Now let's say we want to transition our square into a circle. This is not quite as easy as it sounds. A transition only works on attributes and styles. Unfortunately, there is no attribute or style for our shape property. The shape instead is defined by the element itself. A workaround for this is to apply a border radius to our square to make it appear to be a circle. If we set the Rx and Ry properties to half the width and height respectively, we'll achieve the desired effect. So let's refresh our browser and test this. There seems to be a problem here. Instead of a nice smooth transition from non-rounded corners to rounded ones, the animation just chopped off the corners. The reason for this, and a common pitfall when starting to use transitions, is that there is no initial Rx and Ry value for our rectangle. D3 doesn't know how to interpolate the values from non-existent to 50 and thus forces the final transition value. We could fix this in one of two ways. We could go back to where we created our rectangle and add Rx and Ry attributes with initial values of 0. Or we could utilize our start function and set them to 0 there. Let's try the latter. Now if we test this, we see, voila, a nice smooth transition from a rectangle to a circle. Finally, we'll use everything we've learned so far to create a third step to our animation. Have our now green circle fade out and remove itself from the canvas. We'll do this by initializing an opacity value in our start function to 1. Then we'll create a second end function to fire when the second transition ends. The second ending will transition the opacity from 1 to 0 and use the remove method to delete it from the canvas. D3 is smart enough to wait for the transition to complete before removing the element. So now let's refresh our browser and we'll see the lovely dance of our square in its entirety. We should now feel confident with using the D3 Transition API. Besides a few potential complications to watch out for, it was relatively painless. In the next couple of videos, we'll see how our chart can benefit from some transitions. Now that we feel comfortable using transitions in D3, we're going to apply what we've learned to our ever-evolving scatterplot example of export data. As we saw in the previous video, D3 does most of the work for us by interpolating between points. So this should be a relatively easy video, which will be a nice change of pace. We'll start by naively adding transitions to our circles and then to our axes. This will be a very quick process, so afterwards we'll take a hard look at our visualization and try to resolve some of the issues that are created, as well as adding some simple aesthetic improvements. In the meantime, let's dive right on in. We'll start with the completed code from section 6's last video. We'll copy this into a new file, say index 7, and skim through the code as a quick refresher of what's going on. We should recall how we've structured our update function to be separate from our initialization code, thus enabling us to listen for form updates and fetch a new pair of years data. So here, where we're drawing our circles, we'll simply add a transition and duration method before setting or updating the CX position. Now we can test this in the browser. Nothing's different about our first draw, but if we change one of the years, we'll notice how our circles now transition into place. Pretty nice for adding just 2 lines of code. We can do the same for our axes. We'll find the lines where we update our axes and simply add the same 2 lines, a transition and a duration. In order to keep our code a bit more modular, we'll define the duration time above and store it in a variable, so if we want to change it in the future, we'll only need to change it in one place. Now that's smart coding. So let's refresh our browser again and view our changes. It's really amazing just how much heavy lifting D3 does for us. Our axes transition beautifully, scrolling in and everything. The last transition we need to add is for our labels, which are not activated by default and may have gone unnoticed. But even activating the labels, there is a problem. Looking at the error console, it's failing to find the mouseover function. This is because the transition breaks the chain of command to the on handler, which no longer gets the circle's parent. So let's reselect the circle after changing all of the attributes with the transition and add the mouse over and mouse out handlers. After reloading, if we select the labels checkbox and change a year or two to update the scatter, we'll notice our labels aren't sliding around like our circles. They're jumping into position first, then the circles follow. This is not good at all. So let's go ahead and add these 2 simple lines where our labels are being updated. Now if we refresh our browser, we'll see that our labels move around our chart in time with our circles, since everything has the same duration. There is still one minor bug remaining that you may have encountered. It is that when we mouse over a node, if a portion of a label is on top of it, it will block the mouse over event from firing. This is due to the fact that since we are drawing the labels last, they are on the top of the nodes and thus blocking the event. A simple fix to this is to set pointer events to none for our text elements in the CSS. The last few things we want to do are more bug fixes and enhancements. You may have noticed on the initial draw, our nodes fade from black to their respective color. Why is this? Well, the circles don't have an initial color when they're created, and the browser defaults to use black as their fill, so D3 fades them from black to whatever their proper color is. We can resolve this and optimize our transition a bit by simply moving the code for setting the radius and the color to our non-transitive circle selection. We've now completed adding a simple transition to our scatter plot and fixing a few bugs while making a tiny enhancement. Our job here is done for now. Coming up in the next video, we'll be gracefully removing points with transitions. We'll finish up this section by adding a few minor improvements to our scatter plot to complete it. This video is much lighter on code since much of the heavy lifting of adding these transitions is really taken care of by D3. But there are still a few nuances to be aware of. We'll start out by looking at what it means to stagger our transitions and the reasons why we would want to do so. Then we'll focus on removing nodes that are missing data for one of the specified years requested. Finally, we'll add a specific transition just for exiting nodes. The first nuance we'll add, which though slight, can make a huge improvement on understanding how a transition is working. This is referred to as staggering the transition. Staggering means that not all of our elements are moving to the new destination at the same time, thus minimizing occlusion that could occur from overlapping nodes. This allows the user to focus on tracking one element at a time if they wish to better understand the transition as it is occurring. Viewing our current demo, we see that it's a bit hard to pick out any single node and view its movement. The way to stagger our transition is to add a delay, which we explored in the first video of this section. But we don't want the delay to be the same for every node that we are moving. Instead of passing a single value, we'll pass a function that will determine the element's delay based on its current index in the array. You can think of this as its place in the queue of transitions about to occur. We use the variable I as the value for the element's index, and we divide it by the total number of elements to make it a percentage of how far along we are. And then we multiply this by whatever number of milliseconds our transition is. We already have this value set in a variable, so all we need to do is use it. Run this in the browser, then change a year to trigger the transition. You should see the circles move one at a time. Of course, it's still quite fast, since the total animation time is only 700 milliseconds. But with regards to viewing the changes, this is much easier to view segments moving at a time. What happens when we have labels turned on? Let's check the box and see. Whoa! They jump to their final destination. And with the transition? Well, they smoothly went to their destination, but well ahead of their staggered circles. Let's add the same delay to our text nodes to ensure that they move in tandem. Reload, select a couple of years, then change the year and submit. Hey, it works! However, it's still kind of annoying seeing circles stacked up against the X or Y axis for certain years. This is caused by them missing data for the opposing axis, thus resulting in zeros for that year. A nice enhancement here would be simply to filter these data points out before we draw them. Easy enough. We can use the built-in filter array function to trim our data array. Let's refresh the browser and see the results of our change. Select a couple of years, change them. It's all good. Those annoying lingering circles are gone. Sure, we've still got the minimum value for each axis riding the opposite axis, but that's to be expected. Still, this is a subtle yet impactful aesthetic update to our visualization. Our last stop on this journey of transitions is adding an exit transition for our discarded nodes. This way, instead of them just disappearing, they'll fall off the bottom of the chart. Similar to the enter function, which returns an array of SVG groups that don't yet exist, the exit function does the same for groups that no longer have data. These were objects that were removed previously, but we'll store the exit array in a variable which we can reference in two places. We'll first delay the removal of our exiting circle and text groups by 3 times the duration. Then, after a delay of just 2 times the duration, we'll have these circles fall to the bottom of our plot with a bounce effect specified by the ease function, adding a bit of flair. We can now run this in the browser and see our beautiful exit transitions bouncing to the bottom of the page. We've now completed adding some advanced transitions to our scatter plot, fixed a few problems, and added a couple of embellishments as well. While this section did not require too much coding, it shines a light on how powerful and impactful transitions can be. We'll start working with maps from the next section on out. Welcome to Section 8 of the video course. Chances are you may be asking yourself, when am I going to see some maps? This being a course on visualizations, we would be much remiss to overlook these most familiar of all visualizations. After all, we are shown maps from early on, in grade school, in advertising, on the news, and of course, all over the web. Yet, Just because something is ubiquitous doesn't necessarily make it the best form for conducting information. The main problem with geographic maps as an information visualization is that 3 of the 4 means of encoding information visually, shape, size, and position, are fixed, leaving us to only vary the color values. Thus, looking at a map of the world, Russia, China, Canada, and Greenland always seem to dominate our attention, solely due to the fact that they have gigantic land masses when projected in 2 dimensions. Smaller countries, like the Netherlands and Israel, go largely unnoticed due to their comparatively smaller area. This first video about geovisualizations will walk you through how to fetch raw geographic data from the Natural Earth repository and use command line tools to transform these proprietary file formats to a format digestible by D3, the GeoJSON format. Though this step isn't strictly necessary, since there are many repositories online for pre-converted GeoJSON files, it is a good idea to be able to know where the original source of the data comes from in case we wanted to make some specific customizations for our own map. We'll start by visiting the Natural Earth site. The site is entirely a labor of love. As programmers and not geographers, we should be thankful for the hours of work that went into the original compilation of these raw coordinates from country outlines to city longitude and latitudes. From the top, click on the Downloads tab, then Cultural under Large-Scale Data, then the Download Countries button under the Admin 0 Countries header. Unzipping and looking inside the folder, we'll see the following files. The only one we're really interested in is the .shp or shape file. Our next step in converting this shape file is to download a piece of software called GDAL, a helpful command line utility. You can visit the official website, which has links to precompiled binaries for all major platforms. If you don't yet have it installed, please pause this video while you download and install it. It's okay, I'll wait. On the command line, let's next run ogr to ogr with the -f GeoJSON parameter to output to countries.json from the input file ini10 admin0countries.shp. Now we have a GeoJSON called countries.json. If we open this in a text editor, we'll see the following format. It is important to note that GeoJSON is just JavaScript that uses a specific language of keywords. The main JSON object in GeoJSON is a gigantic object called a feature collection that contains an array of features, which are individual feature objects. Each one of these features represents a country. You can see each country's name as well as many other items, such as 3-character country codes, and many, many more. But the part of the GeoJSON that gives the actual data of the coordinates is the geometry. Within the coordinates are sets of longitude-latitude pairs, each one as a 2-value array. This is the information that cartographers have spent generations compiling and refining. It is important to note that longitude is always listed first. So even though it's common to hear people say latitude-longitude, in GeoJSON it's longitude-latitude. Now there's one more optional step to make our lives much easier. That is to convert our large 25 megabyte GeoJSON file to hold just the information we need to display the countries. We do this using the TopoJSON program, a tool created by Mike Bostock that eliminates redundancy, resulting in a much smaller file. The installer for TopoJSON relies on Node's package manager, or NPM. Most web developers have this as one of their tools in his or her toolbox. So if you don't have it, there are plenty of websites out there that tell you how to get it and install it. Installing TopoJSON then requires the command npm install -g TopoJSON. Again, if you need to install this, just pause the video and start me back up when you're done. Now let's call topo.json to output to topo_countries.json using su_a3 as the identifying property and assigning the property name to name in all caps from the countries.json file as the final parameter. We are able to reduce the size to nearly 10% of the original, going from just under 25 megabytes to a little under 2.5. Although it may not seem like much was accomplished in this video, we have now taken a raw shape file and converted it to topo.json format with about a 90% decrease in file size. As a final step, let's move our topo_countries.json file into our working directory. In the next video, we'll feed this to a D3 function that will convert our longitude-latitude data to XY points so that we can draw a map. Now that we have our geographic data in a JavaScript readable format, we'll show how to actually draw the country outlines via D3. Since this is a data visualization course, and not just a geographic mapping course, we'll want to tie in our export data API information from the previous sections to create a choropleth of export data for a particular product. You may be wondering, what exactly is a choropleth? Surely you've seen one before, but may not have been familiar with the term. A choropleth is essentially a geographic location shaded by the intensity based on its corresponding data value. For example, we wish to map the export data to our world map with the higher export value of a country having a darker shade of color. Here is an example of the final product we are going to produce, with the color of each country corresponding to its export value of coffee. We could have chosen any product here, but for now I've just chosen coffee at random. The steps we'll take to produce the previous map start with loading the topo.json client side via an AJAX call. Then we'll explore the D3 API to see how we can utilize its many geographic functions to help draw the country shapes as SVG paths in the browser. Finally, we'll reuse our AJAX code from the previous videos to request export data from the OEC API and map those values to a color scale. So let's get started. Copy the template HTML file to index8.html. Changes we need to make here include setting the title in head, removing it from the body, and including the topo.json library, which allows us to convert our topo.json back to GeoJSON. What? Hold on! After all the trouble to convert it from GeoJSON, we're converting it back? Well, while topo.json allows us to store our longitude and latitude coordinates in a more concise format, we need to convert them back to GeoJSON for the browser. You can think of topo.json almost like a compression algorithm, similar to zipping a file to save space, but then unzipping it later when we need to use it. We can save bandwidth by only transferring the compressed version. Next, we're going to write a simple outline of how we want to structure our program. This will help us wrap our minds around the task at hand and not get overwhelmed while focusing on modularity. We'll start with our map object, which will hold our global variables. We could also create getter and setter functions for these, but for now, let's keep it simple and just store them in an object. To find out where we found the product code 0901, we can visit the OEC API documentation, which has a list of all product codes used throughout the site. 0901 corresponds to coffee. If you'd like to use a different product for your sample, please feel free. Personally, 1806 would be an excellent choice. Next is determining which aspects of our code need to be executed on page load and which can be done later. The first thing we need to do, of course, is initialize our SVG canvas. It may be tempting to think that we could first draw our map when the page is loaded, and then color in the countries based on the data values in our drawMap function. But the reason we are unable to do this is because we can only bind one set of data to an element at a time. That being said, we can still fetch the topo.json and store it in our map object for future use. This way, we are only making this AJAX call once per page load. Since this is an asynchronous call to the server, meaning that we don't know when it will complete, we need to call our drawMap function within the callback. Our drawMap function is the meat and potatoes of our program. So again, it would make sense to outline the steps we need to take before we begin. Our first step here is to ask the OEC API for data. The rest of the steps are indented to show that they can only be run in the callback of this asynchronous request. Now, as mentioned earlier, we need to merge our data values with our geometry data. After this, we can finally draw our country shapes as SVG paths and color them according to their mapped values. Let's start by using our global year and product variables to set the URL string to the OEC API. Within the callback, let's call a merge topo function with exports as a parameter. Then down at the bottom, let's implement the function to merge our topo.json with our API data. We're first going to iterate over our export data and pull out the country IDs as well as the export value. We need to subtract the first two characters from the country ID to match our topo.json country ID and be sure we convert our export values to floats. Next, let's iterate through our topo.json countries, assigning the export value as a property of the country's properties object. There's something special going on here. We're not using a for each loop, but instead a sum loop, which allows us to short-circuit logic to stop searching through the topo.json when we find the matching country. This can save us many CPU cycles and make our code a bit snappier. This next step should start to look familiar. We are binding our map.countries array as our data. For the D attribute of our path, remember this is a tierce mini-language used by SVG to draw custom paths based on lists of x-y coordinates. We call a D3 helper function, D3.go.path, which does all the heavy lifting for us, converting our longitudes and latitudes to xy coordinates. As an argument, we pass the type of geographic projection we would like to use. Here we use the Mercator coordinate system used by Google Maps and probably the most common on the web. But there are many others available. In fact, there is a whole repository devoted solely to D3 geographic projects, which I encourage you to pursue at your leisure. Finally, let's set the fill attribute as an update function. We need to be sure there is export value data for the country we are setting the fill for. So let's set it to white if it doesn't exist. We do this because different browsers handle an empty color differently. Chrome uses black. With this fallback color, we're saying that white means no value is present. Up at the top of the script, let's declare the color function as a D3 linear scale from an off-white to a dark shade of green. We'll need to set its domain only after the data has been fetched, since the domain depends on the minimum and maximum of the export values for the particular product in the particular year. And with that, load the page in the browser, and we can view the final result. Wow, it looks like Brazil exports a lot of coffee. We now have a basic skeleton for our choropleth map, mapping product export values to the intensity of color for each country that exports a specific product. We will continue to improve this in the next few videos, from integrating user input with a timeline and product dropdown to zooming and adding back our trusty tooltip. Thanks to the enter, update, exit paradigm of D3, our job of adding user input controls becomes much easier. Basically, we've already laid the groundwork for being able to update our map. Hypothetically, all we have to do is open up the console, change our map's year variable, and redraw the map. But we can't expect an end user to feel comfortable opening up the console and entering commands, so we should utilize the browser's built-in input method. That is exactly what we are going to cover in this video, creating input for users to update the map and adding hooks to our JavaScript to listen for these changes. We'll start by using a new HTML5 input called a range to allow users to update the year of the data we are viewing. We'll also create a drop-down and populate it with all the possible products from the API to allow the user to choose from. We'll then listen to each of these input change events and call our drawMap function with the updated data. Finally, we'll embed the user's selection of year and product in the URL via a hash, which we can use to create a permalink. That is, a link they could share with friends that will remember their selections. In our previous video, we simply appended the SVG to the bottom of our content div, the only HTML item in our page. Let's take a little more control this time by adding a div specifically for our SVG map to live in, along with the appropriately named map ID. This will help us stay organized as we're now adding some front-facing inputs. Of course, we'll also want to update where we're initializing our SVG element in our script, changing the selection appropriately. Right above our map container div, we'll add an input of type range. This is the new HTML5 input device that creates a slider on the page. We can specify the minimum and maximum values as well as the interval that we'll allow. So let's set these to go from 1995 to 2012 with a step interval of 1. We'll also set the initial value to 2012. If we load this page in our browser, we'll see this new input device. There's just a bit of a problem here, other than it not affecting our visualization. It would be nice to show the user what value the slider is currently set to, and to have it update as we move the slider. So let's add another input above our slider in the HTML source. This will be a text field that we'll set to read only so that the users cannot manually change it. This will be our readout for the year. Now, to actually make this text update as the user changes the input value, we'll have to add some logic to our slider listener. So in our init function, let's listen for input events on the timeline. Then set the year input to the value of the timeline. Viewing this change in the browser, we can see our text box change as we drag our timeline slider back and forth. Let's move on to our product dropdown. This is a bit more complicated since we'll first have to ask the OEC API for a list of products. But we need a select HTML tag to put them in, so let's add that to our HTML. Now for calling the API. We'll also put this in our init function, similar to how we called the API for a list of countries in the previous video. But this time we'll ask for a list of HS products. HS stands for Harmonized System, which is just a particular classification of products. Once we get this list of products, we'll want to filter out anything without a display ID. Then, using the D3.enter function, we'll append an option element to our product select container. The value attribute shall be the display ID, and the text gets set to the product name. Now, refreshing our browser, we can see our dropdown, which will take a second or two to load, since it's pulling the data from a remote server. One issue you may have noticed is that our dropdown is initialized to horses, not coffee, the product we are actually showing. After our timeline and dropdown initialization code, let's explicitly set them to whatever our map object says it should be. The selection option needs to be done at the end of the options callback. Let's do the same for our timeline and year display, just before setting the listener. This will come in handy later when we hook these up to actually change the map's data. Reload, and great! Now coffee is selected in our drop-down on the page load. Although this isn't a course on CSS or design, let's add some simple CSS just to make our page a little cleaner. We'll center our content div with a width of 960 pixels. We'd also like a smaller year text box and to align our product dropdown to the right. This won't change how our page behaves, but it will make it a bit easier on the eyes, just like when you comb your hair in the morning to look better. Now we have to actually hook up the change events for the two inputs to our map. This is actually easier than it sounds. As mentioned earlier, leveraging D3's inter-update data functionality takes care of most of the heavy lifting. We can just select our timeline, then add an onChange event listener to set our map object to the newly selected year. Calling drawMap will then refresh the map. We'll do the same for our dropdown. Listen for the onChange event, set our map's product key to the new selection, and call our drawMap function again. Easy peasy! Testing this in the browser, we'll see we now have a fully interactive map visualization. The last thing we're going to do in this video is add the ability for users to share exactly what they are currently looking at by embedding the year and product selection in the URL. Using background AJAX request to fetch data is both a blessing and a curse. It is a blessing in the sense that it allows for a much more seamless user experience, but it can be a curse because the page's state is never saved, at least not by default. This means that once I've manipulated the page in some way, changed what I'm looking at, as soon as I refresh the page, all my changes are gone. So in order to explicitly save these states, we're going to write them to the end of the URL as a hash. Something like the following would be what our page's URL would look like. There is no standard function to read and write these hash query parameters to the address bar. So we are going to have to write two utility methods, getHash and setHash. GetHash takes a key parameter and will return its value. Otherwise, it will return all keys and values as an object. setHash, which requires a key and a value, will put the specified key and value into the URL's hash. Let's start by creating the getHash function down at the end of our script. We'll get the URL's current hash as a string and remove the actual hash character. If this is an empty string, we're done and can return null. Otherwise, we need to loop over each key value pair and split them at the equal sign, adding them to our hash object. If the user requests a specific key, we'll only return that value. Otherwise, we'll return the whole object. Now for the setHash function. This will actually use the getHash function to see what is currently set in the browser. We'll then loop through each of the items in the returned object, serializing them in the key1 equal value1 ampersand key2 equal value2 format. Finally, we'll set the URL's hash to this string. With the two utility functions created, let's now add two simple lines to our onChange events. We'll add the year key value pair to our hash in the timeline slider change handler, and add the product hash to our dropdown change handler. Let's test this out in the browser to see it in action. Okay, great! It all works! Our URL is changing as we're updating the UI. There's just a slight problem here. If we copy and paste this URL into a new window, our specified year and product are not used. Well, that's simple to fix. In our init function, we'll simply override our map object year and product defaults if they're set in the URL. Load the page in a new tab, and now everything works. If we were to publish this live, we could easily share our selections with friends. We're now that much closer to having a really amazing and powerful geomap visualization. Our only remaining steps are adding the tooltip, which we can reuse from the previous section, a legend to explain how we are mapping colors and values, and the big kahuna, click to zoom. No more squinting at Europe. We'll actually be able to zoom in and see exactly what these smaller landmass countries are exporting. For this final video in Section 8, we're going to add some finishing touches that will make our geomap really shine. Zooming and tooltips are things we take for granted when using sophisticated mapping software like Google Maps. But these require an extra level of complexity that we'll add in this video. We'll start by adding a click event to our country paths to trigger a function that will zoom our viewport to the specific country we've selected. Next, we'll reuse some of our code from the scatterplots to add a tooltip when hovering over a country. Finally, we'll add a rudimentary legend corresponding to the color scale. This video will most likely be the most complicated we've covered so far, so don't be worried if you don't understand everything all at once. Starting with our zoom function, the concept is quite simple. Basically, we need to attach a click event listener to our country paths that will then call our zoom function. How the zoom function will work is a bit trickier. Luckily for us, there is already a great working example that Mike Bostock, the creator of D3, has made available. Let's take a little detour and view this example. Learning from other people's code is one of the huge benefits of working with open source software. While we may not know exactly how a particular function works, we can study it and try to wrap our heads around its basic functionality. Since our application isn't exactly the same, dealing with a world map instead of the US only, we need to know how to reappropriate this code for our needs. By looking at the code, you'll notice he is creating a group element to which he adds all his state paths. A click event handler function named clicked is attached to each state path. This function first checks if the element we clicked is active, meaning it's already zoomed in on. If so, we call the reset function. Hey, this is a toggle! First click zooms in, second click zooms out, or resets. The next part of the function is a little more complex. First, the bounds of the clicked paths are found. Then the proper scale and transform is calculated to pass to the root group element. Mimicking this, the first thing we need to do is create a root SVG group element under which all of our country paths will be contained within. Zooming will actually just be scaling and translating the root group element. Let's start by creating the zoom group and updating our draw function to use this group instead of the parent SVG. We'll also want to attach a click event to our country paths. Next, let's copy the actual zoom code from the example. We can paste this in at the end of our file. The first thing to change is the function name to zoom, as we named it in our click event listener. All instances of width and height stored in our public object map also need to be updated. Next, we need to replace the instance of G to be map.zoomGroup, as it is named in our code. Finally, there is one more reference to the G variable in the reset function, which will also need to change to map.zoomGroup. Oh, and active needs to be declared at the top of our script to just be a null D3 selection. The path projection declaration can also be moved to the top and referenced in our drawMap function. Now if we refresh our browser, we can test our code and see how clicking zooms us right in on a country, and clicking the same country zooms us out. Taking a peek at the elements themselves, we see everything in our zoom group. The next thing on our list is adding a tooltip so that we can see the exact values of each country as we hover over them. For this, we're going to reuse code, but this time it's our own. Much of the tooltip code we wrote for our scatter plot can be reused for our map. So let's copy that. First, we'll paste in the actual HTML from our tooltip. Here, we'll want to trim some of this since we'll only be viewing one value and won't be showing the continent. We'll also copy and paste in the appropriate CSS, make the table 100% wide, and remove the bottom border that separated the two axes. Next, we'll copy over the actual mouse over and mouse out functions. There's quite a bit of refactoring that we'll need to do. First, let's put this into a separately named function that we'll call tooltip. Mostly we need to change how we access the data to display in the tooltip itself. The logic of how it works is fine. Starting with the country name, instead of returning country attributes sub d.id sub name, we'll want to return d.properties.name. Doing the same for the three-letter abbreviation, we'll replace it with d.id. And we can completely delete the continent setter. Next are the year and value functions. We'll use map.year and d.properties.exportValue respectively. Notice that we format the currency number. We'll have to remember to copy and paste that function in as well. Other than the width and height being properties of map, the rest of the tooltip code can stay the same. Remember, this is all the logic one needs to change the direction the tooltip is drawn if our cursor is too close to the edge of the screen. Finally, we need to call tooltip on mouse over, which we can do along with updating the fill style. On mouse out also needs to be handled the same as before by setting the tooltip's display style to none. With that complete, let's test it in the browser. That works! 2 polished functions down, 1 to go. That leaves us with creating a legend. We'll start by creating a placeholder div in our HTML. Now, due to the fact that we are using a continuous linear scale, we need to figure out a way to create discrete values so that we can make our legend. We could divide our values by the number of buckets we would like to have, and then use our color function to determine what the corresponding color would be. But luckily, there is a D3 scale called quantize that does exactly what we're looking for. So our next problem is that we need to find a set of colors to use as our range. Since we're dealing with discrete values now, we'll need a discrete number of colors. There just so happens to be an open source tool called Color Brewer we can use to find a great set of colors specifically for the purpose of mapping data. From the site, Color Brewer is an online tool designed to help people select good color schemes for maps and other graphics. We can explore and find whatever colors we're interested in, but for now, I'll stick with the greens. 7 of them. We'll also want to add an unordered list to act as the legend within the legend div. In our draw function, we'll need to update our domain, since we could use the drop-down or slider to change our data. We'll then assign our scales range as the data for the list items. Next, we'll enter and update the legend items with the colors and values they correspond to. In our enter function, we'll set the border color to the hex value of our data using the string function, which will just return the string of our color. Finally, we'll set the text to be the lower and upper bounds of the bucket the color corresponds to. By using the color scales invert function, we can get the data value given a color. We'll use our currency number formatter to print out the values. We have to scroll all the way down to the bottom of the page to see the legend. And once we currently can't see the colors. So let's add some CSS to make our legend a bit nicer. Reload. Okay, great. Now it looks much better. Of course, we could spend much more time designing this, but for now, let's leave it as is. And with that, we're done. We have a fully functional choropleth, complete with zooming, mouse over tooltips, and a legend. We came a long way to get here. First starting with raw coordinates, converting them to GeoJSON, then TopoJSON. Then we began mapping them via D3 and creating a fully interactive year slider and product dropdown. We'll go even further than this with a geo scatterplot in the next section. It's a bit sad to say, but we've reached the final section of the video course. As a brief recap, we can think back to how much we've learned and realize the magnitude of content covered in these 8 sections so far. We started with the basics of JavaScript and how the D3 library API is built on top of it. We learned about using D3 not only for HTML elements, but also for creating SVG elements. We built a robust scatterplot that queried an externally hosted API for data and added user interface elements. We also learned the importance of animation in interactive visualizations, and most recently, we applied our knowledge of building reusable charts to creating an interactive choropleth with zoom behavior and UI elements to update the data. So in this final section, we'll combine everything we've learned so far to create a novel visualization. what we'll call a geoscatter. Think of it as a combination of our scatter plot from a few sections back with our geomap, so that instead of using circles to represent a country, we'll actually use the shape of the country in our chart. We'll start with the code from the last video of the previous section. We'll rearrange the HTML and CSS a bit to accommodate the new controls we'll have, such as both an X and Y axis controller. Next, we'll go into our JavaScript and revisit our UI element handlers. We'll utilize a new library called Q.js, also maintained by Mike Bostock, the creator of D3, to enable us to dynamically create a queue of AJAX requests, all with a single callback function called on completion. Finally, we'll add some logic to merge our export data with our geographic data. As stated, we'll start with our code from the previous section and build upon it. Let's make some quick stylistic changes. We'll create a left side column, let's call it Controls, and have our visualization, viz, live on the right. Within our Controls div, we want to create two UI sections, one for our y-axis and the other for our x-axis. Because these both have similar controls coming over from our previous visualization, we'll need to distinguish them by changing IDs of year, timeline, and products to be the classes of each, but with a parent div of y and x respectively to maintain uniqueness. In the CSS, we'll set our controls and viz divs to float left and specify their widths. We'll set our year and slider next to each other as well. If we were to load the page in our browser, not everything would work properly, but we would get a sense of our visualization's new layout. So let's turn to our global map object and update the variables that our UI elements will be updating when they are changed. First of all, we changed our visualization's width in our CSS, so we need to change our map's canvas width to reflect that. The height should be reduced appropriately as well. Our product and year values will now be objects in and of themselves with X and Y key value pairs. We'll also add a new key called updated, so we'll know if the user updated the X or Y variable. The map's year and product initialization will now have to be broken up to cover their respective X and Y subvalues. The respective controls themselves also need to align with the new global map variables after initialization. Then we have to reflect these changes in our UI event listeners. We also have to change their D3 selection to use classes instead of IDs. Since both our X and Y timeline sliders use the same event listener, we'll need to determine which axis the user wishes to update. As we had planned before, we'll access this via the parent node's ID. We'll also explicitly set our timeline and text to the current year. Finally, we'll initialize the X and Y selected product values after the product options are populated. Updating our currently selected product when one is selected follows these same modifications as the timeline change handler. Now if we refresh our page, we'll notice that our page is still getting an error. If we look closely, it is due to the fact that we're trying to set the data API URL to use the map.product and map.year variables, which are now objects instead of values. But this doesn't matter for now. We're just concerned with the UI functionality. And that part works. The product list is being populated, and changing the year and product sets our permalink URL hash properly. We won't worry about repairing our data API quite yet, since we're going to change how we're making AJAX requests soon. It's now time for a short detour into how to handle those AJAX requests. The Q.js is a small library to help us maintain our AJAX requests using logic to determine if they need to be requested. When the page is loaded, we'll obviously need to make all the requests. But as the user changes their selections for the specific AJAX, we'll only need to fetch that specific data and not all requests. This problem arises because AJAX requests are asynchronous. For our visualization to be drawn, we need to wait until they've completed. The Queue API is quite simple. We can view the documentation from the GitHub page. Basically, the two functions we need are defer and await all. Defer takes the D3 data fetching function, such as D3.js, as its first parameter. The second parameter is the URL of the data to fetch. Queue's await all function then accepts the callback function from the D3 data fetching function, an instance called for each returned asynchronous task. We'll need to include this library before anything. So in the document's head, let's insert the D3.js org hosted version of the file. Now we'll make our JSON requests using the Queue API. Well, actually we won't worry about our HS requests for our dropdowns, since the execution of this callback does not depend on any other requests. But the rest of our data calls, one for geography, one for the x-axis, and one for the y-axis, will depend on each other's completion, so we'll queue them. Let's create a new function called updateData to be called anytime a user element changes. Each request will only be added to the queue if it needs to be. The geography will only be fetched on page load, and the axes data requests will only happen if something is updated. Finally, remove the JSON fetch of the topo.json toward the start of the init file. Instead, call updateData at the end of the init function to get it all started. Now we need to update our drawMap function. First of all, the queue's callback will call drawMap with the error and data parameters, where data is an array of the results from the 1, 2, or 3 requests. With that, we'll next need to comment out the entire body that we have and add logic that checks which requests were made and thus which data has been fetched. If the length of the returned array is 3, then obviously this is an init and all requests were made. If there are 2 items returned, this means that the data contains only y and x-axis data in that order. The case in which 1 item is being returned is a bit more complicated, since it entails knowing which axis was updated. Since either map.update.x or map.update.y will be true, we can simply use this and reset both back to false afterwards. Because we're going to need to persist our data over multiple calls, the data object in our map is also going to have to be initialized at the top. Let's initialize data's x and y to be empty arrays to start. Finally, armed with our data, we would like to filter our list of countries to only the ones with data for both axes. We can do this by using the JavaScript filter function on our array of countries. We'll first determine the lowercase ID of the country and use this to filter both our x-axis and y-axis data arrays to find the current country. We'll then check if both data arrays have a length larger than 0. If they do, we'll set this country's export data to an object with this country's x-axis and y-axis data. A return value of true from filter means that the data is not filtered out. When we run this in our browser, we can check that it is working by noticing that the first number, the total number of countries, is larger than the second number, the filtered number of countries. We've now completed a lot of the initial groundwork and planning for our geoscatter visualization. In the next video, we'll look at some of the intricacies with drawing our country shapes at specific x-y coordinates instead of the ones specified in the GeoJSON file we are loading. Now that we've laid a lot of the groundwork for our geoscatter, that is, we've fetched and filtered the data, we are free to begin thinking about the implementation details of how we will draw our countries as points in our scatterplot. The biggest hurdle along this journey will be the fact that our topo.json has specific longitude-latitude positions which are traditionally translated to xy coordinates for drawing countries in place. Here we are going to hack the locations to be specific to our data so the locations will no longer be geographically correct. We'll start by just drawing our country shapes on the page, reminding us of our work from the previous section, Section 8. Because countries can be made up of many polygons, think Alaska and Hawaii, which, though part of the United States, are not geographically connected, we'll need to find the largest polygon and use that as our distinctive shape for that country. Another issue we'll have to account for is the aspect of our countries being different sizes. We'll want to make them uniform in size so that Greenland doesn't appear 10 times larger than Israel on the scatterplot. Finally, we'll complete this video by plotting a given country to its XY position in correlation to the XY values from our data. For testing purposes, we'll adjust our filter countries function to return only a subset of 4 countries, so we can more rapidly prototype our code without being overwhelmed. Next, given our filtered countries, we'll assign data to them. Then, using our enter function, we'll append groups to which we'll add paths into the SVG canvas. Our geographic path generator has already been declared at the beginning of our codebase. Now, loading this file in our browser, we'll see something like the following. Notice how the 4 countries we're showing are located in their geographically correct place, and also that many of our countries have non-contiguous shapes, such as Alaska and Hawaii for the US, Corsica for France, and Sicily and Sardinia for Italy. So we're going to need to find some way of determining the largest polygon from each set of multiple polygons. We'll use the following function, conveniently included with the course files in the findlargest.js file. Include that in the header. Dealing with some of the nuances of this function is a bit beyond the scope of this tutorial, so we'll use this piece of code as a black box. That being said, it is important to have a surface level understanding of what is going on. The basic gist of what is going on in this function is that we are looping through each of the coordinates and sorting them from largest to smallest using the path area function. After we find the largest polygon, we then need to change the geometry type from multi-polygon to polygon. Finally, we run our data through this function and through our path generator to draw it on the page. Now if we refresh our page and wait a bit, we'll see that Alaska and other islands have disappeared. Our next step is to have each of our country's shapes be of the same size. Let's go with 100 pixels. We'll do this by using a transformation of the scale property on our paths. First, we need to find out which is larger, the width or the height, and find the scale factor by dividing 100 by that dimension. Another attribute we'll want to set on our paths is the vector effect to non-scaling stroke, so that the border doesn't become out of proportion. Finally, we need to apply a translate transformation on our shapes so we can have them appear at the XY values corresponding to our data. Since each of our paths is in a group, we'll apply the transformation to the group. We can start by just trying to get our paths to the top left origin of our SVG 00. To do this, we'll use the handy getBbox function, which has attributes for the computed x, y, width, and height of our shape. So by translating this, that is, moving our shape to the negative value of our x and y positions, we'll now have our shapes move to 0, 0. To make the canvas area clear, let's put a red border around it. Hold on a minute. Remember that in a scatter plot, the position corresponding to your 0, 0 value is the bottom left, not the top left? The new y value just needs to be the height stored in our map variable minus the calculated y value and the box height. Save that and reload. And we're now at the proper origin. In the meantime, we'd like to add our export data values. To do this, we need to make a scale to map our data to the pixel dimensions of the screen. We've already done this many times in the previous sections, so this should look familiar. We'll define the scale toward the top of our code, where we initialize many of our other variables. The y scale is where we flip our origin so that it maps values from height up to 0. Then we'll update the domain of the scale to the extent of the data for each axis so that anytime the user requests new data, the scale domain is updated. Finally, we can call the appropriate scale function on our data in our translation function to move our data points to the appropriate xy coordinates. Remembering here that we need to add the scaled value to our x value and subtract it from our origin located y to handle the difference in direction of each axis. Now if we refresh the browser, we'll see the positions of our countries correlate to our data. The only problem is that we don't see Brazil or Italy. Well, if we inspect our canvas, we can see that they are being drawn, only that they are now off the screen. This is because on our scale, these two countries have the highest x and y values, and using our coordinate logic, we are drawing them off the screen. That is something we'll solve in our next video, as well as adding in axes. In the meantime, we've completed the second video of our final section. We now have our country shapes being drawn in the data correct locations, resized proportionately, and filtered so that we are only using the largest landmass for a given country. I would recommend interested parties spend some time reading through the Find Largest function to see exactly how it is working, and possibly improve its efficiency. Next, we'll complete our new visualization by adding back our axes from the previous sections, as well as our tooltip and legend. Well, it looks like we finally made it to the last video. Getting to the end of things is always a little bittersweet. The intention of this video course was never to be a completely comprehensive lesson of everything you could possibly do with D3, but instead as a sort of overview, using best practices that you yourself will be able to put into action on your own projects, whether they be personal or business related. So let's jump into this last video. In this video, we'll start by solving the problem we left off with the previous video, that is, our largest countries by export value getting displayed off screen. Once that issue is resolved, we'll add the display of our axes to officially make it a scatterplot. We'll follow that up with adding our tooltip back as well. Finally, we'll add a checklist of country names which we'll fetch from the OEC API to allow our users to dynamically select which countries they wish to compare. We'll conclude with what we've learned in this video and summarize the next steps for interested parties. Determining how to solve the issue of making the bounds of our chart incorporate extra room on both axes is not necessarily intuitive. We might think we could simply hard-code a buffer of a certain size, but this potentially leaves too much or too little room on our chart. The way we're going to solve this problem is to feed a specific buffer size, half of our shape's width for the x-axis and half of our shape's height for the y-axis, to the start and end of our scale using the scale's invert method. This method essentially calculates a new domain based on these values. We can read more specifics about the invert method for scales on the D3 wiki. Once again, we're going to start off where we left off in the code of the previous video. If we load our file in the browser, we'll quickly recall the problem we were having when we left off. We should be seeing 4 countries, but we're only seeing 2. When we use the inspector, we see that our largest scales are off the chart. So the way we'll solve this is by changing the domain of our x and y scales to extend the buffer 50 pixels in all directions. Finally, let's adjust the final translation to center the country at its given point on the scatter chart. Now if we view this change in our browser, voila! We see all 4 countries. Each one goes to a different extreme. Next, let's work on inserting our axes. After removing the red border we are using for testing, let's copy and paste in the axis CSS from our scatter plot from section 7. Then we need to add a new key to our map object, axis, with both an x and y value initialized to null for now. We'll also need our fancy superscript array for formatting our log values, so let's copy and paste it too. With that preparation out of the way, we'll create our axis SVG element in our init function right after where our SVG is appended to the page. Finally, we'll add the code to update the display of our axes when our data is updated in our drawMap function right below where we set our scales to the domain of our new dataset. Now if we refresh the browser, we'll see our axes showing up and updating as we change products we're viewing from the drop-down list. The next thing we'll add back is our tooltip functionality. The CSS and HTML portion we'll copy and paste from section 7. We can paste the HTML over the current tooltip preserved from section 8, since it more resembles what we want with two axes. But let's drop the continent line. After replacing our tooltip HTML and CSS, we'll uncomment our country paths update and snip everything but the mouse over and mouse out handlers. Our tooltip code will then need a bit of an update for our current dataset. The country name and abbreviation can remain as they are. It's just the year and value that needs to be modified to handle X and Y values. Now if we refresh our browser and move our cursor around, we'll see our tooltip. Looks like everything works. It must now be time to drop the code we added for testing. To only show 4 countries, comment that out, return true, and take a look at our visualization. Now we're allowing any country that has both an X and Y value to be shown. I think most people would agree in thinking that this is quite overwhelming. So how could we filter some of this visual clutter and allow a user to see specifically what they are interested in? To answer that, we'll turn to a design UI solution. We'll create a list of checkboxes with each country and allow the user to select only the specific countries they may be interested in. Just as we had chosen 4 countries earlier, now a user can choose any combination the user likes. For this, we'll have to make another API call to the OEC to fetch a list of countries. But before we do that, let's change the HTML and CSS for the legend of the country list to see how it looks in the browser. Now to dynamically populate this list, we'll use similar logic to how we're loading our product list. Let's remove the dummy items from our list. Then we'll make a JSON call for countries just before the call for products. In the callback, we'll create a div with a nested label containing a checkbox and a span of text for each data point. We can view this in the browser and see our list of countries. Next, we need to add logic to redraw our visualization with the selected countries. In the onChange event handler, we'll simply call our updateData function. The drawMap function then needs logic to determine which countries to draw based on the checked checkboxes. The only problem is that when we go to run this in the browser, we get an error. If we trace this to what is causing it, we see that it's where we're determining which new data has been fetched. When we wrote this function, we didn't think of the possibility of no new data being fetched, which is the case here. So we'll add one more if statement to the final else statement, and that should remedy this error. Now for one more final improvement. Wouldn't it be nice if you could select a continent and have all the countries selected so that we could compare them all at once instead of selecting one at a time? Actually, before we get to that, there is one more issue. That is, when we uncheck a country, it is not exiting. So let's add an exit. Now, where were we? Oh yes, selecting continents. Well, this can easily be added to our onChange logic. We'll set the class of each checkbox input to the continent it represents. If the selected item's ID's length is 2 characters long, we'll select every input that begins with those 2 characters. That is, those countries in that continent. Now that's handy! Now we have a pretty impressive and most importantly, unique visualization under our belt. As for the next steps, which someone who has followed this whole tutorial should be able to handle, add in the selected countries to the URL. This would require refactoring the set and get hash functions to allow for serializing a list of elements. When the visualization loads, it would then use this list of countries to initialize itself instead of starting empty. Transitioning the countries to new locations when control selections are changed would be another great exercise. As mentioned in the introduction, we've gone through a lot here, but by no means is it everything. There's a whole world full of different visualizations and open APIs to work with. You should now have the building blocks to embark on this journey by yourself. Best of luck and bon voyage!